Welcome everyone. My name is Panchenko from Skoltech, and I'm extremely delighted to welcome you at the opening of the 10th anniversary AIST conference. This is a conference on analysis of images, social networks, and text. When we created the conference 10 years ago, the overreaching goal was to create a conference organized by highest international standards, and this was supposed to be a data science conference of a completely new type. And I hope that looking back 10 years from the beginning, we managed to succeed at least to some degree. Let me introduce a few key facts about the conference for those who don't really know. So we gathered an excellent program committee featuring 128 PC members from almost 20 countries, and these are leading and well-known experts in their fields of computer vision, natural language processing, data analysis, social network analysis, theoretical machine learning, and so on. So we introduced double-blind review system so that we are sure that decisions of acceptance or rejections of the papers are fair, and there is no bias towards certain names of the participants or something like this. We also have several local chairs, chairs of the sections, which are internationally recognized stars and internationally known experts in their fields, and they curate basically the selection of the papers. So finally, we get submissions also from different countries. So that would be the goal to increase visibility, but I hope very much that we also get submissions from more and more countries. And you see here an example that one of our volume is actually published at Springer lecture notes in computer science series. So in the field of informatics, in the field of computer science, this is pretty much a top publishing venue. And European conference or in different fields such as information retrieval, they select exactly these publisher, as it provides you good indexing, good visibility, and we are really proud that we can offer to the author selected for publication this level of supported visibility. Here is a few facts, few numbers about AIST development through time. So the first conference attracted almost 50 submissions, and now we're going up to almost 120. So we are relatively small but focused scientific conference, so we don't try to reach like complete huge numbers, but rather opt for high quality. And over the years, this number basically stabilized, and we have like a core of 100 submissions overall. Let me introduce you a few key milestones AIST reached during these years. So obviously, the first conference was in 2012, and it was held in Yekaterinburg, Russia. And then 2 years after, we first introduced collaboration with Springer, international publishing house, and we got and entered CCIS series. Next year, 2015, we reached a milestone over 100 submissions, and another year there was another important, very important innovation. This is the introduction of double-blind review system, and also a complete ban on submissions in languages other than English. So as we want to get the maximal audience for our proceedings. So originally the first 5 conferences, in fact, they were held in Yekaterinburg, Russia, and 2017 was the year then AIST first flight and moved to another city. Sorry. And the same year, we also entered the upper top level Springer volume, LNCS, and CCIS series became a volume for supplementary volume. I think an important milestone 2020 was that unlike some other conferences, we managed still to survive and to have the conferences in a full form. Of course, it was online, but we reached quite a big number of participants. And this year we open up and we try to create this hybrid mode conference. Also this year, the conference entered a core ranking, currently only as a regional conference, but I hope that as we go making conferences in other countries and cities, we can also opt for higher levels. So this is really the first conferences AIST also at Russia, and we are extremely excited to and thankful for our host in Tbilisi, so that we can make this nice hybrid mode. Here is a few facts about how we select the papers. Overall, we obtained 118 submissions, but 92 of them were in the end reviewed because of desk rejects and some withdrawals. And overall acceptance rate to the main volume was 27%. So that 27%, and to the CCIS values it was 45%. So overall, we accepted 25 papers to the main volume and 70 papers to the supplementary volume. Here's a list of our chairs. So as you see, you have a composition of experts, both international and some Russian experts. And we always welcome in people trying to help us to organize the sessions. So we will be happy to also see new people here. Here is an important statistics by submissions on by track. So in fact, AIST is traditionally having a lot of presence in natural language processing. In fact, exactly 50% of accepted papers are on NLP. And that's why we organize even a special roundtable, which will be is one of the held as one of parallel sessions on Friday, discussing this strong presence of AIST NLP. It will be chaired by Andrey Kutuzov. But of course, we have quite substantial number of papers on data analysis, machine learning, computer vision, social network analysis, and theoretical machine learning. So here is a few key facts of statistics by track. So you see that acceptance rate is more or less the same, from 23 to 30% by chairs, and of course the biggest number of chairs is also presented in the natural language processing, as we have the biggest number of submissions. Okay, so last but not least, thanks I would like to say to the organizing team. First of all, to the team which is currently organizing this session here in Skolkovo. So we have some professionals set up for organizing of Zoom sessions, and also we have Alexandra Dukhanina, who is and Irina Nikishina from Skoltech, who helped with the organization at our site. Secondly, we have organizers at ExactPro and at Georgia site. So Yosif Itkin is a person who and ExactPro, they provide long-standing support to the conference, and this is really not the first, not the second, not the third time they support the conferences. Without their help, the conference would not sustain, even probably. Also, I help a team of so Natia and Yana, so they were excellent in providing a local organization, and the fact that we have some conferences on Tbilisi side would certainly not be possible without them. Finally, I would like to thank Dmitry Ignatov, who was involved in the organization from the very first day, and he is now in charge of proceedings. So here is a summary of sponsors and supporters. So Tbilisi State University, Skoltech, High School of Economics, Exact Pro, and also Boeing as being commercial supporters. Finally, I just would like to give you a few highlights on how the very first AIST conference in Yekaterinburg, Russia was held some 10 years ago in March 2012. In fact, that was exciting event, and I really hope that the spirit and the atmosphere of the conferences today will have something similar with this date. Many people who were present in these conferences became quite well-known researchers. They now work in different places around the world at different countries in top research institutions, and I'm really not sure why we all gathered in this small conference, but I think there was something about it. Something right, and I'm sure that this tradition will continue. So really, I welcome you. And the final thing, what I want to say is just a few highlights on the most cited papers across all AIST conferences ever. So maybe I missed some papers, so let me know later, but I think I was right. So the most cited paper, which got 304 citations, was a work by Mikhail Korobov. And actually, this is a guy from Yekaterinburg, and he is a developer. He developed a morphological analyzer Pymorphy, and he wrote a paper about it. So that's an analyzer of Russian and Ukrainian languages, and I think they might be having support of more languages now. And in fact, this Pymorphy tool is widely used, and there is no wonder it's cited so much. So many of my students and people performing natural language processing, they're using this tool. So this was a great work, and I'm proud that it got published at AIST. The second paper is by Andrey Kutuzov. It's also very useful development, and it's at a toolkit and actually a repository of pre-trained word embedding models. So this paper got 167 citations, and many people indeed use pre-trained models by Andrey, and they cite this work. So great, congrats, Andrey. The third most cited paper at AIST is by Konstantin Vorontsov, and it's yet another toolkit, open source library, which is again used by community quite widely. The toolkit called Big IRTM, and that's a toolkit published at AIST 2015, a toolkit for regularized topic models. So congrats, Konstantin. That was a really neat work, and yeah, with this, let me finish this introduction. Let me thank all this excellent organizing team, which worked really hard, believe me, all of these months to make it happen. And I welcome you to enjoy the talks and the conference now. Thank you.
Collective work is Professor Manana Khachidze, who is also the head of computer science department there, according to my information. And the talk is called On Georgian Text Processing Toolkit Development. So, dear speakers, please, you are warmly invited.
To get tokens, so tokenization is not a problem. Okay, so Georgian languages, like we do have separating by spaces, so tokenization is not a problem. Subwords is not a problem. Okay, stemming was a problem. For stemming and to find out what okay, so stemming was the problem. Okay, so I'm not speaking about those things that are not problems. So stemming was the problem, and to do a good stuff, stemming thing, we do create this Georgian language database that is having this word and word formations that will help in identifying that these words, okay, which are represented in different forms, are in fact the same. Okay, so that is where this guy's work is helping. And then we have the post-tagging, yes, stuff. And this post-tagger is the thing that we are in development process. You know that the way how post-taggers are created, mainly there are two approaches. One is statistical approach, and another one is rule-based approach. And we actually tried both, okay, but now what we are working on is like we want to introduce a hybrid version, because like we can benefit from some rules and some stuff, because like rules can be applied for other parts of speech that I mentioned, but then we can guess that whatever rest stays is a verb. Okay, so we can identify other parts of speech, and whatever is rest, we can guess it's a verb. Okay, so that's something that we are now in the process of doing. So the rest is actually, that's pretty much actually all that is for the system. So for the parsing, we would go with the top-down approach, and that's like the standard stuff that we can then eventually go with. So I hope that in this, I saw that it was just a very short talk, so I will try to squeeze into it. And thank you for listening, and I would like to answer your question in case you have it. Thank you. Yes, I think that's it.
to Evgeny Tsimbalov, who is the local stage, so to speak. As for the natural language processing track, the session chair is Andrey Kutuzov.
Thanks. Okay, I hope that everyone, both offline and online, can hear me. And we are starting the first session of this year, AIST, and that's session for natural language processing. Thank you everyone who joined us in this room and in Zoom. And I guess the slogan for this instance of the NLP track is Peraspera ad astra. And I really hope that we will get through all these obstacles. Anyway, we have this session from 12:10 Tbilisi time till 2:15 Tbilisi time. We have 1, 2, 3, 4, 5 talks, and each talk is going to take about half an hour and maybe 5 minutes for questions. And without further ado, I think we're really tight on time. So the floor is now, the floor now goes to Elena Tutubalina.
Yeah, hi everyone. Now I will share my slides in Zoom, I guess, and Andrey will help me. No, it's fine.
Okay.
Yeah. Can you hear my school?
Can
you all hear me? Okay, I'll try to speak a little bit louder and maybe. Oh yeah, sure. No, I didn't hide them. It's Windows, so it's not that fast. Okay, I have. It's tricky. Let's try again. At least only me or studio Zoom. Okay, let me start my talk because we're out of time now with our session, and my talk will be about near zero shot classification with a little help from WordNet. This is a joint work with my colleagues from Steklov Institute at St. Petersburg, and the first author is Anton, Alekseev. Good of him to do this amazing job. So let me start to.
Page down?
Page down? No. We're trying to change. Yeah, it's working now. It's a little bit slow on Windows laptop, so please be patient. The goal of our work is to explore the constructive side of online views. It's opinion mining, and mostly all you know that opinion mining is a well-known research area, and a lot of work done in this area about how to select positive reviews, how to distinguish them from negative reviews. But our work is not about sentiment analysis, it's more about subjective information that we can obtain from reviews. For example, how to obtain advices, tips, requests, and suggestions. And for our study, we use reviews about software. A lot of people are suggesting improvements in those specific reviews about software product. For example, how to fix, how to improve the issues, how to fix some problems, and so on and so on. And for models, this focus on zero-shot approaches based on entire models in almost fully unseen zero-shot fashion without any supervision. And why we want to do that? We both know that supervised model works pretty well, but not enough data right now annotated for constructive reviews, for suggestion mining, and so on and so on. And we use data about task 9, which focus on suggestion mining. There are 2 domains: software forums, where a lot of text implies some changes in product, like suggestion in the form of request. Please, can you fix something? Please add this specific function into your app devices in order it to be great, and so on and so on. And the difference in those reviews is the highly technical dictionary which people use, in contrast with hotel reviews. And that slide presents statistics on our data. As far as you can see, it's not very big corporate to train on and to evaluate on. And you also can see that it's a quite imbalanced data. For example, you have, it's a binary classification task. You have suggestion and non-suggestion text. And you can see that only less than 100 texts in this specific corpora represent suggestion class. And plenty of those data is actually not very helpful. It could represent sentiment, it could be positive, negative, neutral, but it's not give idea how to improve the product or how to help hotel to be better. And same specific, you can see training, deficit, and tested. It's tricky how to use this data to train on, also how to find those specific imbalanced data to annotate it and to build more supervised models in order to build good robust models, and how it looks like. Like I already told you, the suggestion in software domain mostly focus on usability issues or with technical issues and suggestion about it. Something happened with my interface, please improve it or not. So some of our task organizers suggest two different steps on how to use this data. Where task A, when you train on the same data, the same domain and evaluate on it, the single domain evaluation basically. And the second task was much trickier and more real world, in more real world setup. Subtask B, where you train on one domain and evaluate on the second domain. So you do it in cross-domain setup, and it's much more trickier. And we also focus on this one. Our work is based on idea from really great work about benchmarking zero-shot text classification models with entitlement models, where you want to use NLI model instead of a classification. And basically you ask the model, okay, this is a text, could you say to me if this text is about this specific label, specific aspect, specific classification? In this way you don't don't fix classification label, and you can basically ask model about anything, and model try to measure how similar this label and this text about this label when you ask about it, and the input, it say, okay, it's entitlement or it's a contradiction or whatever. And we follow this approach in our work, suggestion mining. So the first approach, what we This slide presents our results on two different subsets, A and B, and two different tasks. We don't use any supervision. We use model for entailment and different approaches. 1 to 3. And here you can read results supervised and two. So what you can say, those two approaches do not work well because it's just a simple phrase like the text is suggestion or it's not suggestion. Sometimes it's work even worse than a random baseline. But third approach gives us some hope. It works better for task A because this approach was the optimal set of labels were tuned on dev set from task A and then applied to test set from task A and task B for different domains. So for one results, it's in domain results, and for the second result, it's cross domain result. So here you can see that, for example, the best model for task A obtained 42 F1 measure on test set, while random results give us only 17 F1 score. So it's huge improvement, but still lower than a supervised one with almost 80% of F1 measure. What is interesting that we find out that what you actually have to tune your optimal set of labels on each domain. You can't tune your optimal set of label on dev set from task A and then apply it to task B. And here results about task B that best subset from task A give us almost 50% of F1 measure, but best results were 69 if you have a dev set from your domain. So the set of optimal label made it was not what we expected it to be. This why about it? So the main idea that different domains actually represent suggestion with different terms frequency. You can see what for task B the most frequent label is offer. For task A about software it's actually a request. That is what's expected. And short summary of this presentation. So prediction quality is much far from the supervised searching. So it was quite expected. And several approaches were applied in a full and since zero shot suggestion setup, and models that try to find the best set of labels on how you present your target class with entailment models works better than simple baseline with random sampling. But in order to achieve good results, you have to select your subsets of labels through hyponyms in a WordNet. It's domain dependent. So maybe for future work, we suggest interesting direction on how to find the best set of labels in order to represent your target class. And thank you for listening. If you have any questions, please ask me or write in a Zoom chat.
Yes. Thank you, Elena, for this great effort. And yes, indeed, those who join us via Zoom, please just ask your questions in the chat, because I guess we will just waste more time if we will try to hear your sound. And maybe someone in the live audience have any questions. And I absolutely understand that probably you were distracted a lot, but still. Yeah. If you stand up, it will probably be. Yeah. Thanks.
Maybe it's a bit off topic, but if we're trying to implement this for real life reviews, they consist of like suggestions, local text, some proposal. This is actually how could we say that in real review from this sample to this is suggestion and other is mentioned. If you understand the question, but like how extract the borderlines of suggestions in real review that may consist of like mixing of other species.
Yeah, so thank you for your question. I will repeat it to your audience in Zoom, just in case. So the question was how you select specific part of reviews about suggestion or about different topics. It's a really good question. This same about data was annotated on a sentence level, actually. So we do not try to find suggestion in a whole reviews. So organizer decide that it's better to split sentence per sentence and annotate everything. I think it's worked quite well, but you have, first you have like filtering sentences step because your data is quite imbalanced. You first use classifier to select proper sentences about it. You know that this is a sentence about suggestion. The much trickier and challenging thing is how to find specific phrase like improved this button, improve this like breakfast in your hotel instead of so it's mostly solved by named entity recognition methods when you have to annotate those specific aspects of reviews. And it's also a quite popular topic in opinion mining when you have aspects term about like specific object like breakfast, blue button, and you find those specific words and then cluster them in some graphs. But it's an open question how to do it in a real world setup when you have to update your database in the real world step.
And I believe if we will specify the sentences, they should be in other parts of the text. So we should extract some consistent sentences that goes one by one in a consistent one, not just like sentences.
Yeah, it could be actually. I think you're right too, but in opinion mining research, usually one sentence is enough because there is no storyline. They say like, I do not like your hotel, but it's not quite relevant. You want to find one specific sentence about improve this thing, give request, so it's one short piece.
This is not about a long story. Okay.
Great. Let's thank our speaker again. And we are in fact slightly behind the time. Yeah, Tanya. So let us just change our internet connection. Just wait for 1 minute.
So what will be your recommendations in terms of time?
Be as fast as you can. Yes.
I guess no, because we are running out.
So I don't need a mic. So I'm just talking like that.
It's okay. It's okay. It will remain better if you are yes. Yes, thank you so much.
Так, то есть прекратить шеринг.
Okay.
for the next speaker to arrive to the laptop that we are currently using. Right. Thanks, Sarah. Yeah. So. Okay, let's try to share the screen now. Okay, so let's move on to the next speaker, and with much joy, I introduce Tatiana Shavrina from Sberbank with her talk about bilingual QA system built with Root GPT-3.
Okay, thank you, Andrey. So, together with my colleague, Dina Pisarevskaya, we will be the next, victims of Zoom today. So I will be brief, but I will be happy to answer additional questions. And just for the record, let's check the sound. Do you hear me? And Dina, can you check the sound, please?
I can hear you, and can you hear me?
Yeah, we can.
Great.
Just use page.
Okay, so then let's begin. So today I will be speaking about the bilingual QA system and bilinguality in QA in general, built with Root GPT-3 model. No, it's not. Yeah.
Yes.
So
don't touch the touch screen, just use Twitch. And you can look at the large screen.
Yeah,
because that's what we can see.
So bilingualism and even multilingualism in general, has established itself already as the major topic in NLP. As it provides the test bed for transfer learning in NLP and gives us the possibility to test the model abilities to transfer skills and knowledge between languages. And in terms of question answering, it has its additional task-specific value, as it provides us the possibility to enlarge the knowledge base, So we don't have the same corpora in any language, and when we use information extraction corpora and when we use Wikipedias in different languages, the information that we get doesn't match. It's a different amount of articles and different content actually, and we want to use them all in our general question answering systems, right? And that's what we get in various works that have emerged recently, and in various test beds and benchmarks in cross-lingual QA like Xquad. But still, the results show that for particular languages, it's better to use not multilingual models, but monolingual models mostly, fine-tuned between the pairs of languages. So for Russian, we don't have so much of variability of these models that could be used both for Russian and for English, for example. And English by now is the most resourceful language for information extraction, for open domain question answering, for information retrieval. So we will be focusing mostly on question answering systems that work for Russian with additional data from the English. Wikipedias and so on. So actually our goal is to create a cross-lingual transfer learning model that can use both Russian and English sources to work best for Russian question answering. But we also test the possibilities of using these models, to perform question answering for English and so on. So this is our additional value, and we have been using the main model, the GPT-3-like model, Russian GPT-3, which is a decoder trained mostly on Russian sources, but it has also used, the Wikipedia from English. We don't have much, we don't have many models else to experiment with, but we have Russian BERT, which we used also as a baseline. I will tell about that later. So talking about our approach, we are using, the fine-tuning approach as usual. And we have been using the standard squad data for English and the SberQuad data set for Russian. They're kind of similar. The format is the same. We have triplets. The paragraph, the question to the paragraph, and the answer is can be found in the paragraph eventually. In Squad of the latest version, in the second version, there are also questions without any answer in the text, and this is like a different class. So we are using that data and translate it automatically to Russian and to English correspondingly. The models we have been using to translate the data are also open source. This is actually Helsinki NLP library. So we are translating the squad data to Russian and SberQuad to English. And what we get is the JSON-like data format with special tokens. So we have introduced, for the fine-tuning purposes, the special tokens that mark the beginning of the sequence, the end of the sequence, and the language, the desired language of the answer. So the task set is that we should use any language, but we can modify what language are we using for the answer, right? So eventually we have trained it in that way that if the language of the question is English, then the answer also should be English. Yes, but the source paragraph can be in any language. So it could be in English or in Russian. So that's the data formats, and we have like 4 types of combinations of languages. Like 2 of them are cross-lingual, from English to Russian, and otherwise from Russian to English, and 2 of them are monolingual, Russian and English. So all these data shuffled gives us about 150,000 training examples with automatic translation. And we have used both the development data to test the models, as they are both available for these types of data sets. So the fine-tuning setup was quite standard. So we used like 20,000 steps of iterations for training the model. Just technical details for the model to be more reproducible. All the source code and the models, they are both available on our GitHub. I will give the link later. So after the fine-tuning of the decoder model, the GPT-3, eventually we got an interesting example. So I have my example on the slides now, but I understand that maybe it's not that much seen. So I will like a little bit read it. This is the text paragraph about the monetary policy of Canada. Eventually, and this is informational paragraph in English, and we modify the language. So the token of the language is Russian, and the question is in Russian. So what's the time period from the moments of description of monetary policy to its realization, actually. And the answer can be found in the English text, not in Russian, of course. And we have the golden answer translated from the English, and we have the answer of the model given also in Russian. The answer of the model is correct, but it doesn't match. So the problem is, like in Russian and like in any question answering data sets, as we are extracting basically the answer from the paragraph, and we cannot do it from the translated languages, from the setup like this, because we have the paragraph in different language, then the model somehow uses to translate, but the translation doesn't, match exactly. So what can we do to, evaluate the models correctly, because we don't want to, punish our models for, answers like that. From the point of view of human, this answer is absolutely correct. But the exact match is like maybe not the best metric. So how can we evaluate the quality of the models that we get? And here I'd like to pass the mic to Dina Pisarevskaya, who would tell you about the metrics we used a little bit.
Okay, at least we will try.
Thank you, Tatiana. Now I will continue. Just in case, can you hear me well? Can you hear me?
Yeah, we can hear you differently.
Great. So now I'm going to tell you about evaluation. So we have 4 steps. In new, it means that word and generated answers are in Russian and text is in English. In question and both answers in English, text in Russian. In question, both answers and text are in Russian. And question and text are in English.
Yeah, it will just take so much time.
And we apply 2 types of metrics. The first type is such as exact fuzzy metrics to different aspects to estimate if a answer is relevant. So I can see the slides.
Yeah, sure. We should change the slides now.
Okay.
Yeah.
Right, 2 types of metrics. And here on this table, you can see our metrics, and later I'm going to describe the main takeaways that we did. Could I ask you to go to the next slide, please? Next slide, please. Thank you. As to classical strict metrics, we see that we set up yields the highest exact match values between both answer and generated answer. And both cross-lingual setups provide better results than the simple English-English setup. Rouge L and Meteor metrics also show the same patterns. It is worth mentioning that among string matching metrics, exact match has the lowest scores. It means that generated answers, especially for MN and cross-lingual setups, may be not presented as an exact citation from the paragraph. It means that the sense is correct, but it can be formulated in a different way. That's why we also use less strict fuzzy string matching metrics. Could I ask to move to the next slide, please? Next slide. Next slide, please. Next slide, please. So can you hear me? Can you hear me? Here you can see that we will demonstrate as results for matching both answer and generated answer using the Einstein distance, and cross-lingual setups have better scores than NN setup. The same also concerns the fuzzy lemmas intersection metric with a threshold over 70%. We also measured special cosine distance between both answers and generated answers using sentence breadth. And if we compare results, English results are lower than cross-lingual UN results, as in other metrics that we already mentioned. Finally, we implemented fuzzy metrics based on named entities intersection in both answers and generated answers. Named entities were extracted using Natasha Python package. We estimated named entities ratio for the whole data set. In addition, we also measured more strictly precision only for generated examples with named entities. An example was considered as true positive if minimum one named entity from the generated answer was presented in the gold answer, and the whole number of examples with named entities in generated answers was considered as true positives and false positives. And as in other metrics, we will set up yields are the best results. But it was interesting that, in contrary to other metrics, English setup results for named entities precision are better than cross-lingual setup results. And what about our baseline and its evaluation? Now, Tatiana will continue about our baseline. Thank you.
About the baselines, we have like the same, absolutely the same fine-tuning setup for Russian bird model, as it has said to be seen some of English data during pre-training phase. So we have repeated our procedure with the encoder model eventually. So what we got is like quite a different quality, like a little bit worse. Still, the main problem was, you know, the model was too easy to abuse, I would like to say so, because here we can see an example, the same text about the monetary policy of Canada, and the language token is Russian. So we are basing on the English paragraph, but we must search the Russian-based answer. And what we get is the exact wording of the correct answer, but found and extracted like in English, while the question is in Russian. So that's not what we wanted. And that was like the major problem with Russian bird, because you know, maybe there's some problem with special talking language, but eventually it didn't like made the trick. So evaluating the baseline, we got like slightly worse results overall. The best of them, of course, are for Russian monolingual, and like quite bad for English monolingual setup, but horrific for cross-lingual approach. So some results for the RUGT3. You know, one of the interesting results for me is that actually some kind of decoder architecture is enough, you know, to make this task work. Because the natural way to do it is implement maybe some encoder-decoder architecture, and we didn't do that. But also, you know, the results that we can get are possible in two ways of interpretation. So, you know, what can happen there is that our metrics are quite good for decoder model, because it somehow learned to make a correspondence between English Wikipedia and Russian Wikipedia, and maybe it helps. But also the second possible interpretation is that it just learned to translate, and that would be like more desirable. So to check that, that kind of hypothesis, we have tried the resulting model on the non-wiki paragraph basis, like from news and from fiction texts. And what we get is actually it's working on the news texts from other sources. So eventually it learned to translate somehow. So this is the example of the news text about somehow like, you know, the gas for Europe, and the question, the paragraph is in Russian and the question is in English. What are two main reasons of the planned shutdown in the text? So the GPT-3 based answer is in English, as we asked to, with a special token, and the Bluebird answer is in Russian as it is just extracted from the text. Both answers are still correct, but we wanted it to be in English, and it's in English. So the GPT-3 model fine-tuned also like it makes it possible to and not of course state of the art as quite good for bidirectional question answering, you know, and with models like this, we can say that we can implement it in the open domain question answering when we know that we don't have English in Russian news sources, you know, not in the knowledge base. So I think that the main result is that kind of skill. We should, of course, like make some few steps, maybe try it on the X-squad data set also, and maybe fine tune. It's like in different setups and hyperparameters, but still it's quite decent. So for the spare quad, in terms of the named entities that are presented in the text, and from the opposite direction, from English to Russian, it's like 75% of the correct named entities that was mentioned in the answers. So still, like from English to English, it's not that good. It's like 28%, and from monolingual setup, from Russian to Russian, it's 83% of correct entities in the answers. So that's actually, we have our source code and models open source on the GitHub. Thank you so much, and I'll be happy to questions.
But unfortunately, I think we have to move on to the next speaker because we are really behind the table. Please just ask your questions after the session or in the chat or in whatever.
Yeah, I can ask them also in the chat.
Yeah.
How, like, you know,
Definitely. The Telegram chat? Yes. Where are you present? Do you follow the Zoom session or? The link is in the AIST web page, actually. There at least. Okay. Thanks again, and
thank you so much.
thank you for your courage and yeah.
Must be a really hybrid mode, right?
Yes, the worst mode possible. Okay, so our next speaker should be Nikita Login, I guess. Am I right? Are you here, Nikita?
Hello, can you hear me?
Yes. Hi. Yes, we can hear you.
Great.
Can you share your screen?
Okay. Okay. Here's my okay. Now I make. Okay. It's full screen. Okay. Okay. Can you see my presentation?
Yes. Yes. Now that's fine.
Great. So should I start or shall we wait?
Yes, please. Yes, please.
Okay.
And you have like 25 minutes, I guess, not more.
I think I'll my presentation will be shorter than 25 minutes.
Perfect.
Okay. Hello, ladies and gentlemen. I'm speaking on behalf of myself as well as my colleague Alexander Baranov from National Research University High School of Economics, and also from behalf of our academic advisor Pavel Braslavsky. Our project is called Jokingbird, and it is dedicated to generation funny variants of news headlines. First, I'll speak about our motivation. The biggest motivation was that funny headlines for news attract attention of readers. And another major influence was The Onion, a satirical English language newspaper, which publishes fake news in order to entertain readers. And this fake news also are humorous and often has humorous headlines that are entertaining by themselves. Another reason was the growing popularity of virtual assistants. And for a virtual assistant, it is essential that communication with it should be human-like. So it is essential to have a sense of humor for this virtual assistant. And if it is able to retell news headlines in a funny way, the users will have more engaging communication with it. I have to say that humor generation is a much less studied topic than humor detection or humor classification. But we selected some interesting recent works. The first one is by Horowitz, and in this paper, the authors tried to train the model to generate headlines in the style of The Onion. They used a rather sophisticated approach using a knowledge model from Wikipedia, and also they synthesized news articles for which they generated headlines. The second one is more similar to our work, as the authors of the second paper also used the same dataset, of which I'll tell you later. And they used a neural translation model and applied it to news headlines in order to predict an edited version of it, which should sound funny from the dataset that I will tell you in this slide. About the data, we had three datasets. The first one is a compilation of different publicly available news datasets. It contained more than 300,000 headlines overall. The second one is the Reddit jokes dataset compiled by Weather and Seppi. It contained a dataset of jokes from Reddit, from Kaggle, and also a set of sentences from News Corpus. And these sentences were selected by authors in a way so that their lexics would be similar to jokes from Reddit. And the third dataset is the most important one. It is a compilation of two datasets of the same structure, Humai Credit and Phonelines, compiled by Hossein and colleagues. And it is a dataset of manual edits of news headlines. It is made by crowdsourcers, and the crowdsourcers were asked to change one word or a multi-word named entity in the original headline so that the resulting headline would sound somehow funny, as we can see in this slide. This dataset contained more than 20,000 items. The items were also graded by crowdsourcers on a 4-point scale, but unfortunately, most edits had quite low ratings. So in order to learn only humorous edit, so we selected only edits with score above than 2, and in this dataset there were only near 2,000 items with such score, as you can see on the diagram. And to talk about our pipeline, we use a modular approach. First, we have an original headline of a news article, and then we select collocations in this headline and mask words in this collocation. The next step is word replacement. We have two models for word replacement. One is unsupervised and it's called dist replacer, and the second one is supervised and it's called bird replacer. After that, we have multiple suggestions of humorous edit for one input headline. And on the final step, the humor classifier decides which variant is the funniest and outputs it. To speak about word selection with collocations, we get all 2 or 3 grams of words from a sentence, and then using retrieved collocation scores, we check if these n-grams form a strong collocation. And if an n-gram is a strong collocation, by strong we mean that it exceeds the collocation strength threshold, we mask the right part of it and push it to the next step, which is word replacement. Our first model for word replacement is unsupervised. It's called dist replacer, as it utilizes semantic distance from word-to-vec model. It searches word-to-vec model for words of the same pose that are distant from masked, so that they exceed the threshold of semantic distance. And after that, it checks if these retrieved words form strong collocations with words surrounding the mask token. If it doesn't form a strong collocation, it is also filtered out. We had two variants of this replacer model. One used collocations from news corpus, so it was called dist replacer news, and the other one utilized collocations from Reddit jokes, so it was called dist replacer Reddit. And on the example here, we can see which alternative collocations were retrieved by dist replacer for this input headline. The second model is called bird replacer, and as the name suggests, it utilized bird model. We used publicly available pre-trained bird models and fine-tuned it on our data. The first variant of bird replacer we called bird hum edit, as we fine-tuned it on hum-created data. It was trained to predict the funny edit on the place of a mask token from hum-created. And the second one was fine-tuned on random masked words from Reddit jokes corpus. In this step, we also used top K predictions as we wanted to include variants that we wanted to include more variants in order to increase the probability of humorous output. And also there were cases when a punctuation mark or a function word would get a high score by bird model. So we additionally filtered these cases from bird predictions. And also we filtered out cases when the fine-tuned bird model predicted an original masked token. And the final step in our pipeline is the humor classifier. We used a publicly available model called Colbert from a study by Anamor, Radnejad, and Zogi, as it had very high reported F1 score. And we implemented, as it has been said, it is the final step in our pipeline. On this slide, you can see how it dealt with the previously referenced example. So it shows the funniest variant where partisan patterns was changed to sleeping patterns. Unfortunately, overall scores are quite low, of which I will tell later. And here are the scores of this humor classifier on the output of all our 4 models. We used a selection of random 1,000 headlines from news corpus and fed it to all our models. Sometimes model could not generate an edit as there were no strong collocations in the sentence, or all the suggestions were functional words or punctuation tokens. So for all models, the count of sentences is less than 1,000. And we also estimated average classifier score on the human-created dataset on which we fine-tuned one of our BERT models. We can see that the overall scores are quite low, but for all models as well as for the original dataset, the score for modified headlines is higher than for original headlines. And that the funniest model is BERT Hume Edit. We also decided to manually evaluate our headlines, as it seemed that our classifier, despite being state-of-the-art, was not very domain transferable. And we also utilized a 4-point scale, as in the original dataset HuMiCredit. But we estimated not only funniness of the generated headlines, but also the grammaticality of them. By grammaticality, I mean how the generated sentences were in line with the rules of English grammar. We selected 200 sentences, 50 from each model output, and evaluated them by ourselves. And on this slide, we can see the results of this evaluation. The funniest model, as in case with automatic annotation, is BERT HuMiCredit, while the BERT Jokes model produced the most grammatical output, maybe because it was fine-tuned on a far larger corpus. And as a baseline, we used a model from previously referenced paper by Weller and Seppi. It was a sec-to-sec neural translation model trained on the same dataset HuMiCredit, and we can see that all our models surpassed the baseline set by this model. However, the score is still quite low, though not as low as with automatic scoring. And we can see that BERT-based models produce funnier output than distributive semantics based. There were also problems with human evaluation, as cap between annotators was quite low. You can see it on the table here. And we tried to do crowdsourcing, but the cap on crowdsourcing was even lower, close to 0 for all criteria. So we decided not to include the results of crowdsourcing. And here are some examples from our funniest model, BERT HuMiCredit. And in brackets, we give the manually estimated funniness scores. We can see that The highest funniness scores are achieved when the model predicts an alternative collocation that somehow changes the meaning of the original sentence. For example, Donald Trump becomes Donald Duck, and French election becomes French toast, which are strong collocations both in funny and original variant. To conclude, we can say that our model is able to produce grammatically correct edits of input news headlines, and that the BERT-based models are more efficient than based on semantic distance from word to vec. However, unfortunately, in most cases, our pipeline still fails to produce humorous output, and also we can conclude that human evaluation is quite a demanding task, and it requires as much planning as planning of the model training experiments, if not more planning. And also one more conclusion is that incompatible collocations produce the most humorous edits. However, surprisingly, BERT-based models do this with more success than the obvious solution with models that use collocates that are semantically distinct from their original words. Thank you for your attention. Your questions are welcome.
Let's thank the speaker. You can hear us, right?
I can hear you, but the sound is very weak.
Well, that's how it goes. But yeah, I guess we have time for one very short question, either from the audience or from Zoom. Anyone? Okay, just my 5 cents. Do you see any like downstream practical application for this task or for these methods? I mean, besides just simple joy of creating funny headlines.
Yeah, I think that the main application is virtual assistants, so it can retell the headlines to entertain its user, and also it's maybe useful for news editors, so they can see how they can how their headlines may be turned funny.
Okay, thanks. Then I guess we have to the next. Anyone wants to have a chat with Nikita, just find him in Zoom or in our Telegram channel, in our Telegram chat.
Excuse me, I didn't get the link to the Telegram chat. Can you send it, please?
There is a link to the chat in the AIST website.
Okay, thank you.
Yep, you can join it. Okay, and our next talk is by Anna Nesterenko and Anastasia Yanina about learning to rank with capsule.
Hello, can you hear me?
Yes. Yep. Please share your
and
screen.
can you see my slides?
Yep.
Great. Hello, my name is Anna Nesterenko, and I'm going to tell you about our with Anastasia Yanina study, learning to rank with capsule neural nets. Self-education and acquisition of knowledge is usually associated with some search for scientific literature, and such paradigm of information retrieval is called exploratory research. An example of such search is search for articles that are semantically similar to an article recently studied by a user. Such scenarios have important features that differ them from usual search. So such search demand can be formulated as a short query, and also a user may be not certain about his information needs. So in this case, the user immediately sets a wide direction of search by submitting a whole document or a fragment of document to a search engine. Of course, now there are a lot of systems specifically designed for scientific search. However, their ranking algorithms are unknown. Some studies state that they are designed for short, well-formulated queries, and that they are based on the number of citations, the presence of words of query in the article, and maybe also author's popularity. So it means they don't work well with document-by-document search. However, the result can be very extensive, so ranking quality is extremely important. And the main way to rank such result is to sort them by semantic similarity. It can be done in two ways. First, using simple metrics, or by machine learning models. Actually, search engines use methods of first type, for example, quotient similarity. And our study discusses the application of machine learning, exactly capsule nets, to problem of text ranking. And my next talk will follow this agenda. First, I'll tell about model itself, then about data and its processing, and of course, evaluation metrics and results. So what about model? Our model is actually based on some choices from another study about CAPS-E model. This network reflects their relationship between the query, the user, and the search results. In our problem setting, similarity measure should be universal, and user information here is redundant. So we trained our net on pairs query result, representing both of them are represented by long texts. So actually documents. So trained in such way, network may serve as seem as a score function, which provide relevance for queries between queries and documents. So every document was presented as a high-dimensional embedding, and contrary to CAPS-E model from another study, we don't learn such embeddings from scratch, but instead initialize them with previously learned representations. About data, I will say later. So, and our architecture consisted from two capsules layer. First layer included K capsules, and the output of each capsule is then multiplied by some weight matrix and sum up and sent as an input to the second layer. So the second layer then perform some operation which is called squashing, and produces the final vector which represents relevance between query and the answer. Then about data. For experiments, we've chosen two data sets. The first one is Archive triples. It has about 1 million papers from archive.org, and the average document length is pretty long. It's about 4,000 words. And for the study, we used 20,000 triples. Triple is 3 papers. Paper 1 and paper 2 are semantically and topically close to each other, and paper 1 and paper 3 are completely opposite. So the second data set is more complicated. It's mined. It's a data set collected from anonymous Microsoft News logs. And for the study, we've chosen its subset called Mine Small. It's like of a smaller size. And the average news article length is much smaller. It's only 500 words. So these logs contain news article information, and also some IDs of news which user clicked before, then suggested news, and impression of the user from this suggested news, which impression is 1 if like the user liked that article and clicked, and 0 otherwise. In this data set, we left only logs with sufficient amount of suggested articles, not less than 10, and to rank not at least 10 answers, and with sufficient amount of relevant and irrelevant answers. So all the texts were converted to embeddings using in several ways. First, doc2vec and the fast text model, and so these models were pre-trained on a dataset from archive.org. These 1 million papers, and the other variant was BERT model, and it was pre-trained on English Wikipedia. And BERT embeddings are much longer, 4 times longer than doc2vec and fast text ones. So then the data were sent to a net, and you can see how the input element of the net looks like. So on the slide, the example of how one log from my dataset converted to 4 network input elements, like history, it's news which user clicked, suggestion is the suggestion, and depression. So 4 history logs, it means like 4 net input elements. So I'll move to evaluation. The model was validated based on ranking metrics that were developed separately for each dataset, and of course traditional ranking metrics. Search results for HIF triples contain only exactly 1 relevant and exactly 1 irrelevant text. So we used only one metric. Recall at 1, it's a proportion of search answers for which the relevant text is ranked higher. So like very simple metric. For mind, we use several metrics and they are more complicated. The first one is recall at k, and I have to highlight that unlike the conventional recall at k metric, we use a slightly different formulation. In our case, recall at k, it's a proportion of answers for which all the relevant texts are ranked higher than all irrelevant. And the key feature is that the number of relevant and irrelevant answers is different for like different search elements. And I mean, chi varies from one net input element to another. So then the average precision at k, here k is also varies. And that's an average value of proportion of relevant texts ranked by the net of the top of relevant text. And 2 conventional metrics is normalized discounted cumulative gain at 5 and 10. During the training model, we used such parameters, and just to mention. And let's discuss the results. So first result about archive triples, it's a simpler data set. And so the average len is of text is high. So that's why we consider only doc2vec and fast text embeddings due to some computation limitations. And we can see that for both embedding options, model reaches high recall at 1. And it achieves almost 93% for fast text embeddings. And we can see from the graphs, from the plots, that the quality of model is increasing along with number of filters. It's like a parameter of net. And because the capsules are able to capture more significant and common text feature with high number of such filters. Then results for mind, and it was mentioned that unlike archive triples, model trains faster with fewer number of these filters, and it's happened also due to shorter length of text. And the best results for embeddings models are all embeddings model you can see on the slide. And we see that results are amazing. However, it's incorrect to compare with existing ones from Mind official leaderboard, because in this article, we solve a bit another problem, and the data from Mind dataset was transformed for our needs. Then we compared our model with existing and widely used methods. As a baseline, we've chosen two variants. The first one is quotient similarity with corresponding embeddings and BM25 function. So about quotient similarity, we see that capsule net outperform capsule similarity by all considered metrics for both data sets. We further compared our net with BM25 function, and it's important to say that BM25 function doesn't use embeddings at all. It relies only back or forth representation. So for HIF triplets data set, we achieved BM25 achieved 73%, and BM25 results are on the slide. So all in all, our proposed similarity measure, I mean capsule net, outperforms BM25 with a huge margin. And moreover, BM25 function applied to our task performs even worse than quotient similarity. So what else we can notice is that rank quality of baseline of quotient similarity and BM25 is significantly better for HIF triples than for MIND. So in terms of recall 1, because it's the only one common metric, and this is also explained, I think, by average length of texts, because for HIF triples they are much longer, and it indicates that baseline functions are more effective for large texts. To conclude, so the comparison results show that neural net has a good quality regardless of number search results that needed to be ranked, or whether there are 2 or 10. And so we proposed an algorithm for ranking exploratory search results by semantic proximity. This algorithm can be seen as a step towards exploratory search systems improvements. I think that's all. I hope my talk was clear and useful for you. Thank you for attention. I'll be happy to answer your questions, maybe on Telegram chat as other participants. I can't hear you. I still don't hear you.
Test.
Oh, now I hear.
Okay, so you can hear us at least. Yeah, it almost feels like 2 separate conferences, sorry. But yeah, we missed the last 3 minutes of your talk due to unstable internet connection here. But we still have the possibility to take questions in the chat, and maybe one short question live if anyone. Yes, I guess you can just. Or you can just come close here and talk into the mic.
Okay. Hello. Hi there. So maybe I missed something, but what the intuition of using capsule networks, not something else. What the intuition behind it?
Before the study, we read a lot of studies about ranking exploratory research results, and not just that. And there was an interesting study which used for search personalization task, exactly Khachidze, which I mentioned during my talk about capsule net architecture. So, and there was said that capsules can capture some similarities of text and of user information, and we decided that it can be appropriate for so for large corpus of texts. Yeah, but actually capsule nets are traditionally used for pictures. So they capture some main features from pictures, but it still works for texts.
Okay, thanks. And yeah, I suggest if you want, you can continue your discussion in the chat. And yeah, so I apologize again for all these technical issues. I do hope that it will become better after the lunch. But for now, we have one last talk for today: Transformers for Online Social Network Language Modeling by Ilya Karpov and Nick Kardashev. And I guess Ilya is here in Zoom. Ilya?
No. Can you see the picture? Super.
Yes, we can.
Okay.
Yeah,
so, and okay. Yeah, I'm going to talk about our model that we call Socialbird, and it's an attempt to apply the transformer model to the analysis of the social network texts. So first of all, I'll just have a quick talk about social network texts. We're supposed, oh, it's not working. Yeah, it is. So we suppose that those are texts written by users of the online social networks, and they really differ a lot. So they have lots of mistakes, lots of special slangs, words came from other languages, most likely English, and lots of domain specifics. So just have a look at several texts that I picked several hours ago and try to check yourself. Can you get the idea of each of them? So most likely, so the first one is some regional group in Perm, and it has some special region aspects that should be taken into account. This is just the research group that is talking about some cluster analysis, vectorization, and we should understand that so it's about science. The next one is about density. And I'm not sure if anyone here knows what is strictly here and convention and get the context. And so on, so on. Another example, so the guy is talking about some weapons maybe, because he writes the pistolet, the IK automat. So no, he's talking about opening his own business. And lots of those problems arrive when we're trying to analyze this kind of text. And in fact, our goal was to create such model that could be adapted to the most of existing natural language processing problems just as baseline, because of course you can create your own domain-specific model that works well for spelling correction, for machine translation, and so on and so on. But if you are using the nicely fine-tuned baseline language model, you can adapt it to any problem, any applied problem that you have and get better results. This is the general idea. So talking about online text, lots of competitions prove that they really look more complex than some kind of literature traditional text because of those problems. But from the other point of view, a text always has an author that has written it. And using the information about the author can lead to better understanding of the text. So first of all, we have a list of different profile attributes like age, gender, city, and so on. And no, we're not using them in our model because that would be too easy. The more interesting block is the information about his network position, because an actor is collaborating with other persons and obtains different contacts. So those contacts encode his position, and most likely people in different areas of the network are really interested in different things and have homogeneity between each other. They are together and they have links because they're interested in the same things. So using this information, we can solve lots of problems and develop lots of domain adaptation for our generalized model. This is the general idea. So Oh, nothing changes. Okay. A very important technical aspect. Starting from this point, we'll talk not about the users, the persons of the network, but we want to talk about groups. In fact, because there are much less groups than people. Secondary, because most of the groups are monothematic, and at least 80% of the groups are talking about one topic, and it makes it easier to adopt such models. So from this point, we're just talking only about groups and models that can analyze groups text. And the first, the simplest model that can be adopted to extract network information is the Jacquard index. It's just written here. So the idea is just to compare the intersection divided by the union of users. And so if two groups have lots of common users and have nearly equal sizes, most likely they're relatively close to each other. And that leads to the following picture. So here we have something like 300,000 most the largest groups in the Contactee network. And our threshold was 5,000 members. All the same, again, first of all, because there are too many groups to make proper analysis in the capable time. Secondary, because 5,000 members is something that brings group from some local community to the global one, because Contactee that's advertising at this threshold. And as you can see, this is the UMAP visualization of the generalized network structure. And as you can see, it has several separated clusters or communities. Those are just the groups talking about highly interconnected in terms of Jacquard index, yeah, and a very large core structure that is interconnected with each other. Our first idea was just to take those domain-specific, most likely domain-specific groups and maybe leaves of this core structure, and to train the separate model for each of them. And in fact, we have done it. We have done it for, sorry. We have done it for gardening, for some policy and religion-specific topics, and found out that at least gardening is really located very separately from all the rest of the user's interests. And if we train the model only on gardening, only on political text, we really have better results, better perplexity, better masked language model prediction, and it really works. But the question is, how to make the continuous model that will be useful for at any point of the structure that we would need to analyze. So our research problem has two big questions. The first one is how to extract network similarity and get the information about our communities from the community structure. And the second one is how to inject this information inside the language model in such a way that we'll get the best result. And we didn't want to train 500 separate models because it will be too long and too clumsy. Yeah. So talking about the first block, we have adopted different indices, and from previous research decided to focus exactly on groups interconnection based on users, and it was proven that this really gives you the group homophily from other pages, and we have adopted several indices. So first of all, Jacquard index, as we have just seen. The second one is just a deep walk, the process of random walking and jumping from one node to another, and then converting this track to some embedding that can be vectorized using classical skip-gram model. Yeah, so this leads to the first part of our network vector. And the second part is the correlation coefficient and its SVD dimension reduction. So the idea is just all the same, but we're not looking at intersections. We're looking at how close in terms of correlation are those groups given their users, and then reduce this information dramatically using the SVD algorithm. And this gives us the information about network, and we hope about regional settings, about thematical settings, and so on. So the second block is the knowledge injection. And pretty much research has been done at this area for last, I guess, 5 years. So several most relevant models here, Georgian that uses the convolutional network model that is being injected just at the sentence level, where we add special information at the sentence token. The Gbird model that does injection at the word level for each word of our input. And a very interesting model, the K adapter, that injects information with list of parallel transformers. I'll just show you several pictures in a minute. And the fourth one, in fact, the most closest to our research, and it was done in parallel by the group researchers Hoffman and Schulze, Jokingbird, and does very simple, similar idea, but utilizes the graph attention network, social network embedding, not the deep walk or SVD as we have done at the previous step, and injects it as additional coefficients at the word level. So you can think of this as adding some additional information at token level, similar to Georgian, but they're utilizing the network embeddings as we're doing in our model, but in a more simple way. You'll see it in a minute. So just a minute about the key adapter. Yeah, so we have different sources of information here. For example, some syntax structure, some fact structure, some general domain-specific knowledge, and we're having parallel layers of transformers that are being trained simultaneously. This is the default transformer, and here we have some kind of domain or information-specific transformer that are finally being joined at the very end. And the nice idea about this model is that you can freeze the general model and get the better results on your final task by adapting these additional transformers. So the structure of this additional layer is as follows. So they take the transformer cell and add additional sublayer connection here. So, okay, that's fine. But the most important is that they're freezing some layers to train additional information more directly. And we borrowed this idea somehow. So our final model is the following. This one is just the classical BERT layer. And this is the traditional output where we have some input text tokenized, and so it just goes directly through BERT layers. Our first model of injection was very similar to the thing that guys from VCGN done. So we have taken the social network layer, just as I have described, and injected it at the first token of the sentence. So each token was labeled with information about the author of this text, who wrote this text. And we're working on groups, so all the texts are written by different groups, and the network vector of this group is injected here. And then it just goes directly to the classical BERT network. A more difficult model is the set layer, as we have called it. So the idea is all the same. We have some network information, and we have added some more visualizations here, but generally, so it's all the same as in the left. But here we have the special set layer that replaces one of the existing BERT layers in the model, and our experiments shows that the higher layer is being trained, the better results you get. And the layer itself looks as follows. So we have a list of classical transformer layers, working not one by one, but in parallel. And we're multiplying the information from our social network embedding with different layers. The idea is that if this embedding stores some information about the regional specifics, the thematic specifics, then it will optimize one of the layers better than the other, and thus this layer becomes some kind of specialized layer for this community or for this cluster of interests. Yeah, and training this model simultaneously leads to creating several highly focused models, but in continuous way, not one by one separately, but all together on one large array of information. Yeah, and we have used 16 simultaneous BERT layers just because otherwise we were out of memory on our GPU. But it looks like if someone has a GPU with 64 or larger gigabytes of random access memory, then you can try training larger list of parallel layers, and most likely it will lead to better results. Talking about the training process. So at the left, you can see the training process of the zero token injection, just the model at the middle at this picture, this one. And this one is the set layer injection. And the orange line here is just the baseline BERT model. And its training process. Yeah, this one is all the same. The orange one is BERT, but just one nuance, we have frozen it because starting from some point of the training, it starts overfitting to our data set. So just to get comparable results, we have frozen the model after some point of putting data inside. So this is something like this position of this, or maybe this, sorry, I need to check it, position of the classical BERT model, and then just to get avoid of overfitting, we have frozen it. And this is the cross-entropy loss that shows us that adding conditional network information at the zero level just slowly gives us better results, and we can see some difference between those charts, but injecting at the additional information just inside one of the BERT layers leads to much quicker training process and much better results in terms of cross entropy. Talking about the model evaluation. There are two different evaluation tasks that we have analyzed, both of them based on perplexity. The first one is based on groups that were not taken into the account while analyzing, while training the model. So these groups are out of the model scope, and we need to predict what this group will be most likely talking about. Yeah. The second one is the information about groups that were inside our training data set, but their texts were excluded. So we know this group and we know some information about it, but we have not seen the exact text. So, and the results are as following. These are different options of the generating social network embedding. So we can use either only deep learning or Jacquard coefficients or similarity coefficients and different combinations of them. So, and it looks like the correlation coefficient and deep work embedding gives us the best result in all cases. And these are the results on training on those data sets. These are unknown groups, these are known groups on different models. So this is the baseline BERT model, loss function. Just taken from the box, and we are using the RuBERT model here for all our experiments, so it's the initial baseline for us. and train it until the model starts overfitting. These are results for different injection strategies. So the same as on the charts, we can see that SAT injection gives us much better loss process and much better model optimization. Comparing it with the classical BERT model and the existing results. So it is shown on the right table, and this is just the traditional BERT layer, BERT models, 20 layers and BERT large. Yeah, we can see that BERT large just has more coefficients to model the language and more better perplexity. So this is the RuBERT result just from their paper. This is our result of RuBERT being trained on those texts. So we're talking about something like 30 million texts for one epoch. The best result in perplexity is 2.83. So after all the optimizations that we have talked about at the 9th layer of BERT, if we replace 9th layer with the SAT layer, we obtain the perplexity something like 2.62. Two of those models were trained on the same data and had the same baseline origin model. So it's more important to look at the difference between perplexity, not at the absolute values, because it shows us, because absolute values really highly depend on the dictionary size, on the aspects of the original text, but the difference between perplexities of the models trained in the same conditions shows us how a model is capable to adapt additional information. And it looks like, after all, so the network embedding give additional information to the model, and the social BERT injection model can really adapt it relatively quick and relatively high quality way. So just in comparison with the dynamic contextualized word embeddings by Hoffman, they have used something very close to zero token injection, because they have added some additional information to each word, not to each sentence, but to each word, and they have added social network information there. So they made it the statistical test to show their model improvement. We have relatively large and countable difference in perplexity, so which leads to better modeling. In terms of practical relation, so since we're talking about mask language modeling, the best results can be adopted on very short text, because in this case, your just classical BERT model has no idea about the context, so the text is too short, you cannot predict anything from it. Yeah, and in these cases, social network embedding gives you the highest impact. So while you're analyzing comments, you can use this model best way. For instance, if we're having the phrase like masked embankment, the baseline BERT model predicts the autumn embankment, but our model with one of St. Petersburg's groups injected predicts Nevsky embankment, just the river at St. Petersburg. So if we are injecting if we're asking the model who we read today, then the baseline model answers that the correct answer is Korolev. It was a surprise for me. It's an actor and producer, so maybe he even wrote something. But if we're adding the vector of the poetry group, guys that are discussing poetry, we obtain the answer block here, and that makes us happy. So very small context, big something. So the baseline model BERT trained on social network text leads to Big Brother. But if we're training this, if we're inferencing, sorry, this question on SAT model with DS group vector, we obtain big data that leads to some technological process. So after all, we have developed the model of the Kontakte groups structure. And an important thing here that we have done it in terms of the entire network. So we have not excluded some large topics or trained it on a small data set array. So these are all the groups that have larger than 5,000 members inside. So all large groups of Kontakte. And our model shows the entire model, what Kontakte is talking about. We have analyzed and adopted several ways to inject this information and compare them between each other and obtain something like the 8% of perplexity increasement in comparison with the baseline BERT model trained on the same data set. And so these are the results. We have a GitHub repository that I need to update, and I'll do it just in 2 minutes. Sorry for that, but here is the link at the slides for you. And this is it. Just a second. I need to make sound better. Yeah. Yeah, I can.
Cool. And again, we have time for one short question, maybe. Вообще, мы собирались задать вопрос. Илья, вы слышите меня?
Да, прекрасно слышу.
От вас какая-то противоречивая информация доносится, люди из Zoom. Okay, so my question would be, am I right that you evaluated your social BERT only using perplexity and masked language modeling rate?
Yeah, so we have made several cherry-pick examples how to see that it is really working, but our general evaluation was based on perplexity just because we do not have some classical data set in machine translation or wherever it is that can utilize the network structure. In fact, so Hoffman has done it for injecting the information for the archive papers, and they have also evaluated it on the in terms of perplexity, and maybe this model can be evaluated for some classical tasks using just the SAT injection layer. For instance, we can inject here not the social network information, but for example, the topic of the text or the cluster label of the text and get some kind of similar result. But in this case, we will lose the social network information, that there are no data sets to evaluate some classical problem on the social network data, because usually we have data sets for NLP and some data sets for SNA, and they have separate problems. This is the real problem of this research. Yeah.
I guess. Okay, thanks. So another question? Yeah, sure. But just please keep short because we really
out of time.
Please. Yeah.
Okay, I'm from Russia, from Perm, and I have.
So this is about you. Okay.
Yes. And I have 1 petabyte data from Kontakte. And how can I use your model for analyzing
we can continue talking in the chat because we're not really sure if we can make our social network embeddings public, and does it violate some rules. So we're publishing our model code at the repository, but I guess I can share the social network information model with you and to use it. And this is the idea, and we can continue talking inside the chat.
Yeah, I really suggest you to continue this discussion in the chat, either in Telegram or in Zoom or in whatever platform you find suitable. And yeah, so thanks. Yeah, so sorry. So this concludes the first session of today's NLP track. And for now, for the next hour, the online and offline parts of the conference will be split. So the offline part of the conference goes to have some lunch. And I hope that those on Zoom will also have their fun. But yeah, stay tuned. We will continue at 3:30 Tbilisi time, which means 2:30 Moscow time. We will have two great invited talk by Irina Nikishina and Zulfat Mukhadinov. And then we will continue with the second part of the NLP track. So yes, have some rest and see you in an hour. Same Zoom room. All right, welcome back. And we move on with our next invited talk. And it is with great pleasure that I introduce you Irina Nikishina, who is, well, who wears both hats today as an all-powerful organizer of the AIST conference, responsible for numerous victories today that you were, I guess, able to observe, and at the same time as an NLP researcher who is going to talk us about her work in taxonomy enrichment and other interesting stuff. So let's welcome Irina with your applause. Yes, thanks. And the floor is yours, please.
Thank you. Let me see what's going on. No. Нет, я думаю, что так не должно быть. Oh, yes. So, okay. First, let me introduce not only myself, but my team as well. My name is Irina Nikishina. I'm the third-year PhD student at Caltech. My bachelor's and master's degrees are in computational linguistics in the Higher School of Economics. And I've been AIST secretary for the last 2 years, and I'm also, just a small advertisement, that I'm also one of the founders with Andrey Kutuzov of the semantic search engine for the papers presented in the Russian NLP conferences called RUS NLP. And actually, all your papers that you submitted, all your published papers will be added to our website, and you will be able to search for your names and to search for articles that are similar to yours during the whole history of NLP conferences. Here is my team that I'm working together with, and Alexander Panchenko is my supervisor. And there are a lot of nice people working with me. And here is the list of expertise we have published during the last years. I'm not going to read this list out loud, but just be aware of that. Okay, but the last topic that we are currently discussing is that is the toxicity in the social networks. That text can be toxic, that speech can be toxic, and actually people can be rude and offensive and speak in an offensive way, but not only people, but also chatbots. For example, меня зовут Алиса, а меня Игорь, а я Алиса, очень приятно, и мне, а тебе по губе. Как лечить? Эвтаназия. А если по-другому? К сожалению, это все, что я знаю. Только эвтаназия. Только. This is Alisa. Other examples you may read on the slide because they contain swear words, so I'm not going to read them out loud. But the idea is that we need detoxified text. Why do we need them? First, as we can see, we need to clean chatbots from toxicity because if we use some neural approaches, we can generate some abusive or offensive text. So we need to delete this text. Or sometimes people are speaking to each other in a rude and offensive way as well. So our idea is to suggest people to be more polite, and we can suggest some detoxified versions of text like, you're stupid or what? This is a masterpiece. No, we can just suggest the user don't to speak in offensive way and say, no, I think this is a masterpiece. So to be more polite. Therefore, there has been several competitions in the previous years, but we have prepared, our team has prepared something exciting for you. Even it happens really now. Today we start our competition on Russian detoxification based on parallel corpus. Here is the website and the Codalab link. This is the competition adjacent to the next year dialogue 2022. And this is the project made with MTS AI, Sber, and Skoltech. So we very welcome you to participate in this competition. So hopefully we will be able to make our internet a better place by detoxifying text. And yes, we know there has been competitions by Yandex in October and November on the topic. However, they did not provide any parallel corpus to train supervised models, only unsupervised. And we provided and collected in corpus using Yandex Толока to be able to collect parallel text which were verified by the users, which were verified by the content, style, and fluency. So you're very welcome to learn everything about this competition. So that was a small intro, but yes, and we provide baselines. So you're very welcome to join our discussion group on Telegram. And this is how our competition looks like in Codalab, so you be aware of it. Okay, and now we come to the topic of my research that I'm currently doing during my PhD studies. It's devoted to the taxonomy enrichment task with text and graph vector representations. Actually, the name of the topic I'm currently presenting today is the same as the paper that has been accepted to the Semantic Web Journal recently, which is called Taxonomy Enrichment with Text and Graph Vector Representations. And here on the slide, you can also see other papers devoted to the same topic. Actually, but first we need to, when we discuss in taxonomy enrichment, first let us briefly discuss what a taxonomy is. Taxonomy is a graph structure or a tree structure where we have nodes. Those are words. Do I have something like to? Do I have some, I don't know, thing to? Liza, the pointer, yes. This one? No.
It will be visible on the screen.
It's not visible on the screen. Okay. Thank you. Yes. Do you see the mouse? Yes, we have nodes, which are actual words or synset. For example, it's not just words because we can have a word child, and we can have different. We have an object which is child, and we can have different words for this object: child, baby, toddler, etc., etc. It will refer to the same object in the world, the same subject in the world, a child. So we have nodes like objects in the real world, and we have those are called synsets, and we have the relations between them. And the relations between them are actually the two types of relationship: hypernymy and hyponymy. An example: we have two words, apple and fruit. We say that apple is hypernym for the word fruit, and fruit is hypernym for the word apple. In other words, like fruit is parent for the word apple, and apple is like a child for the word fruit. For you to be able to understand this difficult hypernym, hypernym, and not to mix them up. So I would just use parents and children. Okay, so we have relations, and taxonomy actually includes only one type of relationship. This parent-child is a relationship. No other types, unlike other ontologies. However, why do we need taxonomies? Taxonomies might be used in a number of natural language processing tasks. You might see them on the slide. However, the main idea, why do we need our task, which is, okay, we come back later. So now taxonomies are used in various natural language processing tasks. For example, during named entity recognition task, we might refer to WordNet to extract something, to understand that something is a subject or a person or a location, because WordNet accumulates a large number of names, objects, etc., etc. So, but taxonomies are never complete, and they are almost always updated manually. So there are linguists who are sitting and writing down some new words that they think that would be appropriate to add. They choose their own words, or they choose the area from which new words should be added. So actually, they do it manually. It's a time-consuming process. It also requires expertise in the field. So that is why we suggest our task that is called taxonomy enrichment. It's a task of automatic adding new words to the taxonomy. So given words that are not included to the taxonomy, we need to associate each new word with the appropriate hypernym, with the appropriate parent. For example, we have a new word tally, a cat like, we have a new word husky. And as an example, there is a tally, a cat like husky that was raised with cats, and it behaves like cats. And we have this new word husky that you may see on the slide. And the idea is where to put, actually, where we can put this new word. Is it a cat, domestic cat, a white wolf, working dog, etc., etc. So the idea is that we can do it automatically, relying on some data. And why would we need this task? Because, for example, here is a mock-up of a system where we input the new word touch screen, and there are several options. And linguists cannot just manually type these hypernyms, these parents, and search them into the taxonomy. They just can look through the list and mark the correct answers. So it would mean that it would be easier for the linguists to annotate taxonomy and do it faster. Okay, as for the taxonomy enrichment, and taxonomies are very complex structure. If we can just view them as trees, like parent, child, or one parent may have many children, etc., etc. But the problem is the problem you can see on the slide. So the right image for the word hydraulica is presenting the normal case when we have two parents. Those parents are separate from each other: engineering science, applied science, physics, and natural science. But if you take the word moksha on the left, it has two parents, tributary and river. And tributary is a child of the word river. So we have a triangle here. So it's just a mess. So normally taxonomies can be messy, and we should work with this messy data somehow. Or, for example, we have a word domra that has two parents, string instrument, a folk instrument, and those two instruments has only one parent, that is musical instrument. So actually, those structures are very, very complex, and we need to deal with them somehow. That is why we've decided that we would consider as correct answer not only the direct hypernyms, but also their parents, because it would be difficult for the automated system to identify the correct place and the correct number of parents. For example, if I see the word moksha, I would say, okay, this is a river. Or when I say the word domra, I would say that this is string instrument or musical instrument, and any of these answer would be correct. Okay, as for the prior work on the topic, there has been several semi-val tasks on the topic, but not exactly on taxonomy enrichment. Only in 2016, there has been semi-val task on taxonomy enrichment. And last year we organized in the dialogue conference we organized through RUSE 2020 the taxonomy enrichment task for the Russian language. Okay, what do we do now? Now we are discussing data sets. So, okay, we understand that the taxonomy enrichment task is important. We understand how we may apply it. We understand that the structure is complex, but what about the data sets? Okay, what do we need? Where we would get new words to add to the taxonomy with the correct answers. Okay, let us think about the diachrony. So maybe 2 years or 4 years ago, there was WordNet in its previous version. So it has less words, less links, etc., etc. So we have found different versions of WordNet. For example, WordNet 1.6, 1.7, 2.0, 2.1, etc., etc. And here is the statistic of those data sets. So what we can do, we can subtract from the latest version of WordNet one of the earlier versions. So WordNet against WordNet 3.0, WordNet 1.7 against WordNet 3.0, WordNet 2.0 against WordNet 3.0. And we can do the same for the Russian language. Recently, WordNet 2.0 has been published, and we can subtract WordNet 2.0 from WordNet 1.0. And RUSE 2020, it's a restricted version of the Russian dataset above. We included as we just want to compare the results on this dataset as well. Okay, here the example how those datasets look like. For example, we have a word, cyber terrorism, and we have its hypernyms. The hypernyms are listed as numbers, and the last letter is the letter of the part of speech, and there are names for each scene set. And yes, we also did some work to connect Russian WordNet with English WordNet, and the last column is actually some scene sets that has been found in English WordNet. So we have data set. What we can do next? Next, we can apply some approach for that. As the baseline, we applied the method called Ranking Plus Wiki. It's a method published during the Kalin conference also last year, and it actually is as follows. We have a new word, and we can use word embeddings or graph embeddings or any type of embeddings for that. So we can have word and we can have its representation. And according to distributional semantics, similar words share similar context. And in our case, it has been found that there has been several investigations that among those top 10, top 20, I don't know, top N closest nearest neighbors, we can see cohyponyms. Cohyponyms means that the words share a common parent. For example, for the input word banana, I see the closest neighbors like orange, apple, peach, grapes, I don't know, maybe other fruits, and the word fruit, why not? And fruit. And yes, and I can understand that, okay, if I take the words apple, I take the word orange, I take the word grapes, I can look for their parents, and these parents may be considered as parents for my input word that I'm looking for. For example, the parent of the word apple is fruit, so I can say that the parent of banana is also fruit because they share common parents. This is this was the our logic. So okay, we take those closest parents, we get we take those closest neighbors, we take their parents, and then we sort them because, for example, we take the parent of the word apple, it would be company and fruit. Of the word orange, it would be color and fruit. Of the word fruit, it will be, I don't know, maybe some other word, and for the word grapes, it would be also fruit. So then we calculate the similarity to the input word, and we calculate how many times did this word occur. So we calculate that, and we understand, okay, the fruit is the most common and the closest word, and we consider it as our hypernym. Okay, this was the ranking method. And in addition, we can add some features from Wiktionary, like if we search for the word banana in Wiktionary, maybe we can find something. Maybe this word has been already added in Wiktionary, and we know its synonyms, we know its definition, we know its close words. So we search for those words that are our candidates in Wiktionary, and if we find some, we say, okay, we are 100% sure that banana is a fruit. So here is this method, and we improve this method by adding some other features. You might see them on the slide, and there are very many, so I'm not going into details describing that. I think that in addition, I would say that these features are the extension of our features. For example, we considered only parents, but maybe among the top nearest neighbors, we have seen like very common words, very general words, and we need to go deeper. So we consider not only hypernyms, but also hyponyms. We consider not only words, but also lemmas. We can compute the minimum, average, and maximum similarity, and many other features. So we just extended our features, Wiktionary features, and this combined feature from ranking plus wiki by many other features, and we result in 9 numbers as features. So we put these 9 numbers as features to logistic regression model and predict the score, the ranking score. Another approach that we also describe, this is actually the approach which is called web-based Tsintsadze ranking. This approach gained top 1 result on Rousset on the nouns track, and we consider it as a SOTA. However, this approach has an important drawback: weak reproducibility. Actually, it's a method that applies machine translation and the Yandex machine translation system, Google search, Yandex search, and those results are not reproducible. Because, for example, I have my own search history, and I am fond of Apple production, and I want to buy any Apple products. So I'm constantly looking on the websites, etc., etc. So if I search for the word Apple, there will be very low probability that I will occur something like buy apples, some kilograms from the supermarket or something like that. So it's more probable that I will see more something related to the company. So the reproducibility of this method, of such method, is weak, but we still consider it because it's a SOTA approach for Russian. And another approach is hypertopath. It's a recent paper from Kalin from last year. It actually takes one hypernym as input, then it puts it through encoder-decoder model and tries to decode the whole path to the word entity, to the most general word entity. And here you can see the example like pizza, and they use this pizza as input and try to generate the whole chain: dish, nutriment, food, entity, etc., 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 until the word entity. We also apply this approach for our data sets because they test it on WordNet, but not on diachronic WordNets as we do. Okay, now about vector representations. I said that, okay, yes, we are taking some representation, we take some nearest neighbors and do something with them, apply some techniques. But what about those vector representations? Which kind of vector representations do we use? We use, first of all, textual embeddings like word2vec, fast text, and sometimes BLOF as well. And here is just a simple explanation how fast text is different from word2vec, because fast text also applies some information from the word n-grams. And this actually is very effective for the Russian language, because the Russian language actually has a lot of endings that can be changed, but the word would be similar. So fast text actually, to my mind, can be, that is why fast text produce better results according to our results. So here is the difference. And okay, for the not2vec, I cannot, no. Wow, okay. For the not2vec embeddings. Not2vec embeddings are really those were actually textual embeddings, and now we're coming to graph embeddings that we applied. We also applied not-to-vec embeddings, and such embeddings are actually very similar to word-to-vec. The difference is as follows. For example, we have a sequence of words in a sentence or in a corpus, the quick brown fox, and we might easily generate or train a word-to-vec model from this sequence of words. But what can we do if we have not words but a graph? We can simply sample some chains, like sentence chains, from this graph somehow randomly, and use this data as input. For example, we have a graph. We can go with random walks through the graph and generate some input data and then train embeddings. So in this way, from the second part, from input data to embeddings, it's similar to word-to-vec. It's a skip-gram model. And from graph, we can randomly travel across the graph and generate such sequences. Okay, and yes, and this is the probabilities how we travel. So if there are some probabilities to go back to the node that we have already seen, to the new node that we have not seen, or to some nodes that we have already seen that are connected to the previous node. So this is X1. We also tried Poincare embeddings. Those are hyperbolic embeddings. Embeddings that are applied to hyperbolic space and to dimension to n-dimensional Poincare ball. We also tried to use Poincare embeddings because it was, as we know, that Poincare embeddings are really good at capturing hierarchical structure, etc., etc. So we thought, okay, Poincare embeddings might be of use here, so we might apply them. We also tried GCN embeddings. This GCN embeddings is actually a neural network model that actually captures the subgraph, the nearest neighbors of the graph, and we take the target node and we represent this node as the we collect the representation of this node as the convolution of these neighbors, and these neighbors are computed as a convolution of their neighbors. And like the last part, the most right part, are just the embeddings, the input embeddings, like fast text to word-to-vec. Then we convolute those embeddings and get the representation, for example, of B, and then we convolute the B, C, and D, and get the representation of A. So GCN embeddings are graph-based embeddings. So here we thought, okay, GCN embeddings might be of use as well for this task, as well as GAT embeddings. The idea is quite similar to GCN. However, it applies not only not convolution but attention layer. And TADV embeddings, as we have already discussed, not-to-vec, we can view not-to-vec as a multiplication of two matrices. So we need to decompose this input matrix to two matrices, and we can just add another matrix of text to make this not-to-vec be aware of text as well. So if we're not-to-vec doesn't know anything about the text, so we can apply TADV that is actually knows something about text as well, and the embeddings will be much better, and we will see that. Another approach is to combine embeddings somehow. We can combine word-to-vec, fast text embeddings using this approach, IEMI or KAIEMI. We may combine not-to-vec with fast text. We can combine any types of embeddings together. So those are the meta embeddings. The AAEMI, it means that we average embeddings. And KAIEMI means that we concatenate the embeddings. And actually we use autoencoder here. So we want to autoencode the embeddings into some vector space and then to decode them to the initial vectors. And those meta embeddings concatenated or averaged also demonstrated good results. So yes, evaluation part. As for the evaluation, we use the map metric. And maybe these formulas are not very do not very well explain how it works. So here is some example. For example, we have a new word, husky, and we have two correct answers like dog and working dog, because the direct hypernym is working dog, and the second order hypernym is just dog. So we put this Husky free model and have a set of candidates, a set of rank candidates, like dog with probability with score 0.9, for example, wolf with score 0.85, etc., etc. So those answers are actually ranked, and we need to evaluate this ranking. So how well we identified the results. For example, we have 2 correct answers, and we understand, okay, we would get the best score if we predicted all of them closer to the top of the list. So, okay, if we calculate average precision, we calculate it as follows. For example, we take the first word, dog. This is correct, correct. So we divide 1 by 1. The second place, this is incorrect, wolf. So we divide 0 by 2. For the incorrect places, we put 0 in the denominator. And for the working dog, it's correct. So we have 2 correct answers and divided by the position number. So we have 2 divided by 4. Okay, and actually, the average precision here would be one half. One half is we divide by 2 because we have 2 correct answers. If we had 3 correct answers, we would divide by 3. So here we sum all the results, and the average precision score is 0.3333, etc. Okay, so mean average precision score. So we have all new words like husky, like hashtag, like selfie, and we average the average precision for each word. So here is how this metric works. However, as we have already discussed, some relations can be interconnected. For example, we have a new word, cruise, and we need to find the correct parents. The correct parents would be entertaining journey, tour, and journey. And their parents, the like grandparents of the word cruise, would be entertainment, active leisure, travel, and move. However, as you can see, this subgraph, all words are interconnected, so we don't have 2 separate subgraph. We have one graph at all. So it means that for us, it would be enough to predict any of these words to get the highest score. So we allow the model to predict any of these words, because otherwise it would be too difficult. For example, we have a set of direct hypernyms like entertaining journey, journey, and tour. We have a set of direct hypernyms with their parents. For entertaining journey, it's travel, entertainment, active leisure, journey, travel, move, tour, travel, journey, active leisure. And then we connect a connectivity component. So how all those words are connected. And connectivity component here is only N1. Those are all words. So it means that we need to predict any of these words to get the highest score. And the same would work for the word husky, as we have the connectivity component would be dog and working dog, because the dog is the parent of working dog. So for us, it would be enough to predict only dog, and this would the score would be not 0.3 but 1, because we correctly predicted dog, and it's on the first place of the ranked list. Okay, the results. Here you can see the results, and the results has different colors for different approaches. Let me remind you that we have an approach called baseline, and this is the color is emerald. We have 3 baselines on fast text, on BLUF, and on word2vec. We have DV rank. This is actually an improved version of baseline. We have, which is red. We have DV rank graph. So those are the results based on graph embeddings. We have DV rank meta, the results based on meta embeddings, and DV rank meta word plus graph. So when we combine as meta embeddings different word and graph embeddings. And we have SOTA approaches. As SOTA approaches, we consider hyper-to-path from the Kalim conference, and our approach web-based Tsintsadze ranking from the RUSET 2020. Those were the results for English, and we can see that DV rank meta, when we apply both graph and text, gave us better results than any other combination. But for Russian, the situation is a little bit different. So here we can see that different meta words plus graph are not very efficient, and we can just eliminate this graph part and still get good results only on different meta based on word embeddings. So here we just need to combine word embeddings, and graph embeddings does not help us almost at all. And here just the summarization of all the results. We have different types of approaches here, and we can see that for English, different meta is the best approach, where we have words and graph for both nouns and verbs. Then different meta is coming only on words and word embeddings. Then for English, it would be SOTA approach. For nouns, and for verbs it would be DV-rank, etc., etc., and baseline is quite low. Okay, and DV-rank graph is for verbs doesn't work at all. So for verbs, graph embeddings does not perform good results, does not demonstrate good results. As for the Russian, the situation is slightly different. DV-rank meta demonstrate better results, and for verbs it's even much better than words plus graph. Baseline for the verbs is quite strong here, as you can see. And once again, DV-rank graph is not performing very well. Here are some examples. Here you can see why actually graph approaches do not perform well. For example, we have a new word play therapy, and here are the correct hypernyms, psychotherapy and therapy. And you can see that in fast text with DV-rank, IAMI with fast text word2vec and glove, fast text word2vec, glove and TADV, they still are able to predict the correct answer, at least therapy, and for AIMI, even psychotherapy. And for graph embeddings, there are no correct results at all, and they're just random, I would say, like baseball play. Everything is connected to play for graph stage and TADV, and for concurrent not to vec. It's actually, I don't know what's going on here. For the word eyewitness, it's actually almost the same. All of the models based on word embeddings can predict the results, and models on graph approaches only TADV, which actually also incorporates some information from text, some embeddings from some word embeddings still can perform and guess the word watch. Okay, as for the error analysis, so everything is quite understandable, but maybe there are some errors that we can change immediately, and we can understand why the model is not correct. For example, we have the first type of errors when nearest neighbors are semantically close, but not the correct answer. For example, the word delete, we expect the sense get rid of, but we predicted remove delete. This is really close, like get rid of, remove delete. But we predicted remove delete, but it's not enough. We should have said get rid of, so we don't get any score at all. For the word hashtag for the Russian corpus, the same. We expected to see something like tag or label, but we predicted symbol short text. For symbol, it's understandable because it's hash, and short text, I guess hashtags are actually short texts. The type 2, that distributional model are unable to predict multiple senses. This is actually the problem of distributional models, because they actually prefer just the most common sense, because as many times the sense has been seen at the corpus. So we normally we predict something like for the word Latakia, we expect the word tobacco, but and municipal city, but predict only tobacco. For the word Zaporozhets, it's the same. Zaporozhets might be the citizen and might be the car brand. However, our models understand only car brand and know nothing about being a citizen. Another thing is that the system predicts too loud and too broad or too narrow concepts. For example, for the word midweek, we expect to see something like day of the week, weekday, but we predict something very general, like time period, week, day, season. For the word medianka, smooth snake, we expect something like non-venomous snake, grass snake, but we predict like something like snake, reptile, or animal. So we predict something really general. For the type 4, we might have also some incorrect word representation. So nearest neighbors are far from the meaning. It's just that for some reason, for cubic kilometer, we wanted to see something like units of capacity, units of measurement, but predicted something like city, settlement, competition, and sport context. So something that is really far away from the meaning of cubic kilometer, and there is no idea why it did that. Or for the word falanga, we expected like persecution of torture, and we predicted like fish, bean, tree, and wood. No idea. And the last type is unaccounted senses. For example, we have the word emeritus, or emeritus, sorry, I don't know how to correctly pronounce that. As expected senses, we see like retiree and non-worker, but when I Google it and looked in Wikipedia, what does this word mean? It means that actually about some retiree and non-worker that should be some professor or academician. That's, we can say this word emeritus only for academicians. We cannot say this about somebody who works, I don't know, anywhere, and he or she is retired. And the same for the word sepia, for the Russian WordNet. We expected something like C mollusk, but predicted color and dye. And actually sepia could be also considered as color. So these are some inaccuracies in the WordNet and RuWordNet. And actually sometimes the model even knows more than the people do, or the people annotates, that actually proves that our method should be applied, because actually it may know even more than the human knows. Okay, as for the conclusion, there is so many conclusions here, but what I wanted to say that actually we have performed deep analysis of word and the graph vector representations to understand which of them can be applied. And the most common question that is asked, there are so many approaches for knowledge graphs. Actually, taxonomy is a knowledge graph. Why don't you use this knowledge graph approaches? The explanation is as follows. So we tried a lot of graph embeddings, and they did not perform well. And nowadays, all papers about taxonomies, they try to implement somehow textual data and textual representations, because they perform well, because they describe not only some nodes in the graph, they describe some objects or words in the language. So we still need this linguistic information. Therefore, we assume that taxonomies should be viewed as separately from other types of knowledge graph, or we tried to test some methods. And actually, we want to explore methods that they do not rely on predefined candidates. Like, for example, we have a new words to be added to the taxonomy, and this word is already given by us, by someone. But what if we just move the task on the other way around? Like, we have a graph, we have some information from the pre-trained, for example, language models, and we ask the model to predict the correct for something. For example, we have the word milk, and we want to know what type of milk actually can be, like chocolate milk, low-fat milk, I don't know, oat milk, etc., etc. So maybe models already incorporate this information, and we, using the taxonomy and pre-trained language model, we can predict more new words automatically as well. So thank you for your attention. I'll be happy to answer your questions. Welcome. Do you want the mic? Do you want the mic?
Okay, I can just, yeah. Thanks for the talk. So just one minor question first. Why did you expect for the word falanga the senses of torture, persecution? Yeah, and as far as I know, falanga is a military, sort of a military rank. Yeah, with PH, yeah, and this one. And what is this? So that's a torture device, or maybe I just maybe I'm just ignorant about the meaning of the word falanga spelled with F. What is this? Maybe everyone knows this. All right. Okay. Okay.
What is it?
The soles of the feet are beaten. Okay. Okay, I see. And another question, if no one wants to. It really seems like promising, and it would be great if we could sort of infer a WordNet-like structure from vector space models, from vector representations trained on raw corpora. But is it really feasible? Like, can we really hope that there is some hierarchical structure in distributional vector spaces? Because all this stuff with analogies. Yeah. Sorry.
Yes, there are some papers by Anna, I forgot, still can, Anna Rogers, yes, by her, and she said that it has been discovered that there are several, there's still among those analogies, among those associates, we can see co-hyponyms. So because they are interchangeable in the text, so. We take this hierarchical structure from WordNet. So we search for the closest synsets in WordNet. That means, for example, for the word banana, we see the words apple, fruit, etc., as co-hyponyms, and say, okay, let's take from the WordNet the parents of these words. Yes. Language models like transformers, I guess yes, they know something. So this is something that we are currently working on, and we want to discover that. Yes, please.
From your examples, it looks like you work with unigrams only. Do you see any predicament or difficulty with including multi-word expressions in this sort of in your method?
Yes, for the Russian data set we use with unigrams only, but this is just the restriction, the limitation of the data set. For the English language, when we subtract one WordNet version from another, there may be multi-word expression, but they are just joined with underscore. So we work with multi-word expressions in this case, and to get its representation, we average the embeddings of each word. So yes, we work with them.
If I may, there's another one. Which method of aggregating the vectors you think is more effective? You mentioned two, concatenation and averaging. What's the best?
As far as I remember, and maybe as far as I remember, that's it's IME and maybe sometimes SVD. IME actually gets best results. It's averaging. Thank you.
Oh no, we're actually out of schedule right now. Okay. So as far as understood, graph embeddings did not work pretty well for Russian, but works well for English. Do you have any guidelines or suggestion how to apply it to a new language? So basically you have to start all experiments around, like from start, or you can just pick the best model from English or from Russian. Do you have any idea on it?
Yeah, thank you for your question. I guess this actually happened that because I showed, as I showed you, like this structure. In English WordNet, there are no structures like that. It's mostly parent-child, parent-child, or many children, one parent. Very rarely there are two parents. So, but here in Russian language, in Russian WordNet, there are very complex structures like that. So maybe this is something that prevents the model, the Russian model, to correctly identify the hypernyms, to correctly identify the structure. So therefore, I would say that if you want to apply some methods to a new language, you should look into the WordNet first and see whether to see its structure. If it's like parent-child, parent-child, and they are not related like that, so it's okay. You may apply graph methods, but for more complex structure like that, those are just not working for some reason. Thank you. Yes.
Taxonomy is a tree-like structure, so it doesn't have loops. And can we get the loops during the inference when we have something like this? Or it's impossible?
It still has loops. It's a tree-like structure, but not a tree structure, actually, because it can have loops, as you can see here. That's maybe not loops, but they are still interrelated. So in this case, yes, it's not like a real tree structure. It's a tree-like structure, but it depends on the language, because WordNet looks like more like a tree than, for example, Russian WordNet. So it would depend. Thank you.
The talk will be about biomedical natural language processing given by Zulfat Miftakhudinov. Zulfat working at Kazan Federal University as a researcher, and also he's a researcher in silica medicine and one of my great co-author. Let's give Zulfat the word, and please, the floor is yours.
Thank you for introduction. So my name is Zulfat Miftakhudinov, and I work at Kazan Federal University as a researcher and in Silica company, also as a researcher. And and I will present you the work named Drug and Disease Interpretation Learning with Biomedical Entity Representation Transformer, which is actually a set of works devoted to the entity linking problem in biomedical domain. So let's start with some brief introduction into biomedical NLP. In last years, we can observe the exponential growth of the data in biomedical domain. And the biomedical domain contains different data sources. Among them, we can list the biomedical literature, clinical trials, electronic health records, diagnostic reports, lab notebooks, news records, and social media posts. Each of these data sources contains some valuable information and is just waiting to be extracted and used for some social good reasons or for social good. The biomedical NLP has its own challenges. Among them, we can list the variety of textual subjects. It means that different data sources contains different subjects and can be used for different goals. For example, in social media, we observe user reviews on some drugs, and we can use this information for to extract new adverse effects of the drugs. In biomedical literature, we usually observe some new research on the biomedical domain, and we can see some trends and something else. So the second challenge is a variety of contextual communication styles. It means that in different data sources, we have different languages, different language models. So you can never see something presented in the right side of the slide. In biomedical literature, there's actually something obsessive, and the difference in communication styles usually means different language models, which means the problems with adaptation. The third challenge is language specific to medical context, which means that all the data sources differs from the general domain text. It uses some specific language, drug names, the disease names, and so on. And in practical way, this usually means that you need to use some specific language models like BERT instead of BioBERT, and so on. The other challenges is misspelling and ungrammatical sentences and short telegraphic phrases. They more relevant to the social media. And the last one, abbreviations and acronyms, it's relevant to all the data sources, but mostly it makes a problem in social media because people sometimes find out some new abbreviations. They just use it as they wish, and this causes a lot of problems. So this slide is kind of proven that the social media could be used to extract some new adverse drug reaction effects. On the y-axis, you could see the index value that reflects how often we meet some specific adverse drug reaction. And on the x-axis, we can see the adverse drug reactions. And we consider three different data sources. The first one is Twitter. The second one is FIRES. FIRES is data source that contain official reports on the adverse drug reactions, and drug information database also is official statistics database. And we can see that except the middle part of the graphic, Twitter almost the same as the official data sources, and so that Twitter almost reflects the same information at the official statistic and could be used to extract some new adverse drug reaction effects. So let's consider the default general information extraction pipeline for the biomedical biomedical text processing. The first step in this pipeline is usually some data streaming IP, which usually collects the text from the different data sources and collect them into one place. The second step is usually some kind of pre-filtering, where we usually use the classification approach to filter out unrelevant and uninteresting text for us. And the third and fourth ones are named entity recognition and the entity normalization. The named entity recognition finds the spans of interest, and the entity normalization links this found spans to the concepts from the knowledge bases. And additionally, we can include the relation extraction step, but in this presentation, we will consider only the entity normalization problem. So let's pay more detailed information into the entity linking problem in biomedical domain. In example of clinical trials, on the slide you can see 4 clinical trials. Each of them contains condition or disease, and intervention or treatment, and the information about the phase. The task of entity linking is to link the mention, condition or intervention with some concept from the knowledge base. And the feature of the clinical trials data source is that some mentions could be linked with several concepts, and in sometimes mentions could be linked with no concepts at all. The case when the one main mention links with several concepts, we can handle using the named entity recognition, or using some rules to split this mention into parts and link each part separately to the concept. And when we have mentioned a dozen maps to any concept, we can use the threshold-based method, which I will explain later. So let's continue. So the biomedical entity linking also has challenges. It differs from the general domain. The first challenge is that entity linking in biomedical domain is synonym rich. For example, if we consider the concept that's relevant to the aspirin, between the synonyms of aspirin, we can find the acetylsalicylic acid, something like NSC 101, some chemical synonyms. And in general domain, you usually can't meet this kind of synonym richness. The second challenge is diversity terminologies. At the right part of the slide, you can see the UMLS. It's main ontology on biomedical domain. UMLS contains several terminologies like MESH, SNOMED, NCBI, and so on. And each terminology is used also for the different purposes. For example, MESH, commonly used to index the biomedical literature. The SNOMED is for clinical repositories. ICD, for example, used for the electronic health records, and so on. The third challenge is diverse subdomains. As I said, we have several data sources like social media, like biomedical literature, and this usually causes the problems because in each data source we have different language models. And in this case, also the fifth one is long tail frequency distribution. This means that 20% of the concepts covers 80% of the data, and the other 80% of the concepts are poorly presented in the data sets. So, and in this situation, when you train the supervised models, you use specific terminology, you use specific domain, and you use only the concepts that were presented in your dataset. You usually get models that couldn't normally perform on the different subdomains, on the concepts that were not presented in the training sets, and so on. The first machine learning model that were used for the concept normalization is the classification approach. We also experimented with this approach, but we enriched it with the semantic similarity features. For the entity mention, we have two different representations. One came from the deep neural network models, and the second came from the semantic similarity features, which are based on TF-IDF representations. And then we combine these two representations and just used softmax to get the probability distribution over the concepts. So we experimented with several datasets. We used SNOMED, CADEC, SMM for health, and PsyTAR datasets. And we find out, of course, that the BERT-based models give the higher performance. And the other interesting thing was that the more sophisticated deep neural network model you use, the less gain you take from the semantic similarity features. So this actually is the example of supervised model that poorly performs on the new domains, on the concepts that were not presented in the training part. And to overcome this problem, we proposed our model that called Dilbert, and it presented on the work named Drug and Disease Interpretation Learning. The code for the implementation code you can find on the GitHub account that presented in the slide. First of all, we focused our attention in this work on clinical trials. And the motivation to use clinical trials was because it's growing interest of the research and is actually have a poorly structured data and really need to develop some methods to process the clinical trials. During our research, we couldn't find out any datasets, domain specific, and we created our own gold standard dataset, the manually curated mappings between the mentions and the condition and intervention terminologies. So to map the interventions, we used drug bank terminology, and to map to link the conditions, we used the mesh terminology. Our model Dilbert by design is cross-terminological, and we could use any given terminology without any additional retraining, and it's very fast. It could be used for the real-time inference. We used the triplet learning to train our model. Triplet learning requires three texts. The first one is anchor, which is in our case is just mention. The second text is positive text, which is some synonym of the corresponding concept. The third text is a negative text, which is just any other synonym of any other concept. So when we selected these three texts, we just make closer the positive text to the anchor and make away the negative text from the anchor. And in the result, we get the embedding space where the synonyms of the same concept located grouped together, and the synonyms of the other concepts are located in far away. So the main question when you do the triplet loss training is how to obtain the negative examples. We tried several strategies. We used just random sampling and random sampling plus parents, where we used the positive examples additionally the parents of the corresponding concept. We also used resampling, also called hard negatives. In this case, we used the model that was trained using the randomly sampled negative examples to obtain the hard negatives. And the last one is resampling plus sublinks, where we additionally, as a negative examples, use the siblings of the corresponding concept. So at the inference time, our model used AIST library, which could be with GPU support, which actually give us very high speeds on inference time to find out the nearest neighbor. And we use pre-computed embedding matrix for our vocabulary. And when we have mention, we just we link it to the nearest concept using the Euclidean distance. So to the evaluation process. In our previous work, which is called fair evaluation in concept normalization, we find out that most of the data sets contain duplicates between train and test parts. And the intersection between train and test part is up to 80%. And we proposed new method to filter out this, to evaluate in these conditions models. We filtered out the test set, we removed this 80% of the duplicates, and we find out that the models usually drop in the performance up to approximately for 15%. And when we made evaluation for the Dilbert model, we used also the same strategies. We used refined test sets. Let's take a look at the data sets that we used in our research. We used 4 data sets: CDR disease dataset, CDR chemical dataset, clinical trials condition, and clinical trials interventions. The thing that should be noted is that clinical trials, that dataset doesn't have any trained parts. So we train our model on CDR disease and then evaluate it on the clinical trials condition. And we train our model on CDR chemicals and then evaluate on clinical trials interventions. And the thing is that this CDR disease dataset has medic terminology, and the clinical trials condition has mesh terminology. As I mentioned before, the clinical trials data source sometimes has mentions that maps to one concept, that maps to several concepts, and that are mapped to the no concept at all. So we evaluated into sets where we used all the mentions linked to the single concept, and we used the full set to evaluate. As the metric, we used accuracy top 1, and we compared our model with by BERT ranking and the supervised Bayesian model. So the results. The first thing should be noted is that the Bayesian and Dilbert highly outperform the BERT ranking model. And our proposed model, Dilbert, is also highly outperforms on the clinical trials interventions dataset, but slightly outperforms on clinical trials conditions dataset. And here is almost no, there is no statistical difference between the different different strategies of sampling negative examples, but we can see that for the clinical trials condition and the clinical trials interventions, the best strategy was to use random plus 2 or 5 parents. So how to handle the cases where the mention mapped to the no concept at all? We used the threshold-based method. It means we set the threshold, and when we obtain the closest concept, if the distance between the mention and the closest concept is bigger than this threshold, we say that this mention doesn't map to any concept presented in your terminology. And we evaluated 3 strategies to find out optimal threshold. The first one is to set a threshold to the minimum of false positive cases. The second strategy is to set the threshold to the maximum of true positive cases. And the first strategy was to use a weighted average of these first 2 strategies. We evaluated it on the clinical trials interventions datasets. We split our dataset into the development and test parts and repeated this experiment 20 times. The first strategy gave us 79 and 41 accuracy top 1. The second strategy gave us 71 and 77 accuracy top 1. And the first strategy gave us 85 and 73 accuracy top 1. So in the result of this experiment, we would say that the first strategy is the best to use to find the optimal threshold. And the results on the test part, here we considered only Bayer-Bert ranking to compare with Dilbert model. We still have the big difference between the Bayer-Bert ranking model and the Dilbert model in accuracy top 1. But the situation with the optimal strategy to obtain the negative examples is kind of different. For the clinical trials condition, we still have the random plus 5 parents. But for the interventions case, we could see that the best strategy now is just simply use random sampling. But again, there is no statistically significant difference between different types of sampling the negative examples. So we also performed the error analysis. The first one, we find out that in 14 cases out of 99 mentions, we incorrectly mapped our mention to the parent concept or to the child concept. You can see the example of this on the slide. The mentioned brainstem glioma was mapped to the optic glioma by our model, while the correct one was gliomas, and the gliomas is parent of optic glioma. And the second thing that we find out is that the incorrectly mapped mentions usually have the more length than the concepts that were correctly mapped. So conclusions. We have developed a simple and effective Dilbert model that could be used for almost real-time inference. And you can freely change terminology with almost no drops in the performance. We explored several strategies of generating negative examples, but actually we didn't find any statistically significant differences between different strategies. And we performed extensive analysis of our model on 4 datasets. So thank you for your attention. If you have questions.
If you have questions, please write it in a Zoom chat or write to the FAT, and he will answer it. Unfortunately, we're out of time, so we will skip question session. Let's thank the speaker again, and then we will start the next NLP session in 5 minutes, I guess.
And parameters that evaluate and the size of the clusters, parameters that evaluate the clustering as such as a partition. On these statistics, BERT performed better. Comparison with the ground truth. Our data set actually was labeled 80% of the data was labeled, and for labels we could use the names of the website sections from which the data set, from where each text was published. We specifically constructed a stratified representative sample of 10% of the labeled data and used only 20 most represented classes such as sports, arts, theater, concerts, names of the sections like this. And calculated adjusted rand index and adjusted mutual information index for that. You can see that the results are very low. It is explained by the low quality of our ground truth, of our gold labels, which was in the first place the reason why we undertook this task at all. Also, you can see on the bar chart that the existing labels, the labels that we use to evaluate our petitions, are very language specific. Red bars represent English and yellow bars represent Russian texts, or Russian labels that are assigned to Russian texts only. So there is no common ground. It looks like types of events that happen in the Russian world do not happen in the English world. So there are only 1, 2, 3, 4 categories that have text in English and Russian. So culture is about different things, it looks like, right? But it is again the problem of the golden labels that we had. We did not annotate we should have annotated it probably, but that's a lot of effort and we didn't go that direction. We tried to assess quality, vector quality, when we were faced with the very low results for correlation with ground truth. We tested whether whether the vectors were not good for the task or something. No, if you present the model a neural learner with the labels, it returns fairly good results of 71% accuracy, a bit better for BERT, but reasonable. Then we compared the petitions between themselves. How similar you would expect these petitions be. The same data set clustered based on BERT and based on Elmo. Very dissimilar petitions. The correlation is, or the averaged rand index is 0.07. There's no similarity between the petitions. We did not expect that. Then we looked at the distribution of the new labels, and these are the distributions of the new labels. On Elmo representations, it looks like we have 2 different cultural worlds. There's English world and there's Russian world. And BERT managed to see similarities between texts in 2 languages. Manual analysis. In this step of the research, we tried to identify, to assign labels to each cluster. We used 20 clusters because we had 20 labels in the gold set, and also our internal statistics indicated that 20 would be a good pick for K. We used 51 documents from each cluster, looked at these 51 documents and keywords from each cluster to try and assign a label. From that analysis, it looked like for Elmo petition, language differences override all similarity, all semantic similarity that there was in the data. So it can be seen in the previous slide that we have 2 different languages. There's nothing similar in text, but the difference in language. We have only, I think we have only 2 clusters that include relatively similar proportion of our English and Russian texts. We have several clusters that are exclusively Russian, and the rest are English with Russian texts, including mixed code. And there are only 4 clearly identifiable clusters that are hiking, training, well-being and health and well-being, and social activism, including feminism. On Bird petition, Bird behaved more like a true cross-lingual model. It did see similarities between texts in 2 different languages, and it is more interpretable, way more interpretable. It was easier, way easier to assign the label to each cluster. It seemed to be less distracted by noise and structural properties, while on Elmo we have seen clusters that were determined based on formal properties of text like capitalization. There would be a cluster where each text is capitalized or has capitalization there, or has in imperative mood, a verb in imperative mood. And also it was curious to see cultural differences in these 2 worlds in the same cluster. For example, hiking, the cluster of hiking was also very, very well identifiable by Bird. And in the English world, hiking included texts like leisurely strolls around the neighborhood. And in the Russian world, that would include words like glaciers, tents, making fire in the woods, very aggressive. And okay. Well, in conclusion, we have seen that we have performed the task. We have re-annotated the data, and we have seen that Bird and Elmo, multilingual Bird and Elmo behave differently, perform differently on the task. Elmo petition could have been used to identify noise in the data, because some clusters were attracted texts that were clear noise that we did not see in the pre-processing steps, while Bird returned fairly reliable, interpretable, almost expected result. Thank you. If you have any, we don't have time.
Slightly out of time.
Yeah, so yeah, okay.
If you have any questions, please write in the chat or.
Yeah. Oh, probably I don't want to touch that. No.
Actually, I was told that we need to move to another session to track A. So let us go to track A.
Hello? Good afternoon.
Now we're going to continue with the second talk by Anastasia Kotelnikova. Please, Anastasia, the floor is yours.
Thank you. Good afternoon. I'd like to present our work, lexicon-based methods versus BERT for text sentiment analysis. The outline is as follows. First, some words for introduction. Then I'll tell about lexicon-based methods and tools. After that, I'll describe lexicon-based methods adaptation we made and sentiment lexicon syntax corpora we used. The next issue is the explanation of experimental setup and the results of experiments. And at the end, there will be discussion and conclusion. Let's start from some introduction. The performance of sentiment analysis has improved dramatically over the past few years. This improvement in performance is mainly associated with the development of deep learning methods, especially various models based on the transformer architecture, in particularly BERT. However, deep neural networks models are difficult to train. They need large amounts of data Training requires powerful, expensive video cards with a large memory size. The learning process is time-consuming and energy-intensive. Another issue is the complexity of interpreting the results of the models. An alternative are rule-based or lexicon-based methods using sentiment lexicons. They are fast, they do not require training, and are very well interpreted. But recently, due to the widespread use of deep learning, lexicon-based methods have receded into the background. For the Russian language, there are several recent studies of deep learning models for sentiment analysis. However, there are currently no studies devoted to the comparison of lexicon-based methods and deep learning models. We strive to close this gap and compare the fine-tuned deep neural network model RuBERT with two lexicon-based methods adapted for the Russian language, SOCAL and SentiStrength. For testing, we have used 16 Russian language text corpora labeled by sentiment into 3 classes. Let's move to the lexicon-based methods and tools. There are several tools for sentiment analysis on the base of sentiment lexicons. They can be open source, such as, for example, SOCAL, Vader, Pattern, TextBlob, and proprietary, for example, SentiStrength and SentiText. Some words about SOCAL. My tutor with colleagues developed semantic orientation calculator, or SOCAL, a method and a tool for determining the sentiment of texts in English and in Spanish. The sentiment is recognized on the basis of counting the weights of the sentiment words included in the text. A system of rules is also involved to account for the influence of lexical markers such as modifiers, negations, irrealis markers, and so on. Also, we use SentiStrength. Thelwell with colleagues developed it. It is a tool for sentiment analysis of short texts based on the method same name. The tool gives true score from -1 to -5 and a positive score from +1 to +5. The decision is based on a list of sentiment words with weights corresponding to the sentiment intensity. The method also takes into account modifiers, negations, questions, slang, idioms, and emoticons. Of these tools, as far as we know, only SentiStrength has 2 adaptations for the Russian language, but we couldn't find a detailed description of their implementations. In our work, we have adapted SOCAL and SentiStrength for the Russian language. We selected these tools because SOCAL is the most advanced open source sentiment analysis tools, and SentiStrength, despite being proprietary software, makes it easy to adapt to a new language. For this purpose, it's necessary to provide it with a sentiment lexicon of new language and other linguistic resources, for example, lists of modifiers, negations, interrogative words, slang, and idioms. So in our work, we have adapted SOCAL and SentiStrength for the Russian language. Now I'll tell about this adaptation. Oh, sorry, adaptation. The adaptation of SOCAL and SentiStrength to the Russian language includes the following steps. First, morphological analysis of input texts based on RNN-MOV. Then preparation of Russian language sentiment lexicon. The existing lexicons were used to form it, and I'll describe them later. A peculiarity of SOCAL is to take into account only nouns, adjectives, verbs, and adverbs. Then preparation of Russian language lists of modifiers, for example, очень, едва, значительно, and negations, such as, for example, не, без, невозможно. They were obtained by translating the corresponding SOCAL and SentiStrength lists, as well as by adding Russian language synonyms. The next is the preparation for SOCAL of Russian language lists of irrealis markers, for example, ожидать можно, modification of the SOCAL source code for processing texts with the results of Russian morphological analysis, and organization of programming interface with the desktop version of SentiStrength, submit input texts and process its results. Now I'll tell about the key resource for the considered sentiment analysis methods, sentiment lexicons. The performance of sentiment analysis depends on the completeness and accuracy of such a lexicon. We have used 9 publicly available Russian sentiment lexicons: Rusentilex, WordMap, Senti-Ruskol, MLX, Liniscrowd, Klinovsk, Kotelnikov, Chenskinos, and Tutubalina's lexicon. 2 of them, MLX and Chenskinos, are Russian versions of multilingual lexicons. In this diagram, you can see the total number of elements and the proportion of positive and negative elements in the lexicon. Each lexicon has been processed as follows. We have removed neutral words, words that are both positive and negative at the same time in the lexicon, and words containing Latin letters. All words have been converted to a lowercase and normalized using RNN morph. We also used the voting procedure of these lexicons to build a set of 8 combined lexicons. Only those words that are included in at least n sentiment lexicons are included in the n lexicon. Thus, Lex 1, for example, includes all sentiment words that occur in at least one lexicon. Lex 9 turned out to be empty. Not a single item is included in all sentiment lexicon at the same time. The characteristics of the combined lexicons are shown in this table. Now I'll tell about another lexical resource, text corpora. For evaluation, we have used 16 public text corpora labeled by sentiment, including corpora of reviews about books, movies, cameras, as well as news articles of the seminars RAMIP of 2011 and 12. Then corpora of reviews about cars, restaurants, as well as tweets about banks and telecoms of the seminars Senti-Rueval 2015 and 16 and Semival 2016. Then the RU sentiment corpus containing posts on Vkontakte, and Liniscrowd corpus including posts and comments from Live Journal. Corpora characteristics in this table. The corpora have different topics, sizes, train test split proportion, and the proportion of texts of different classes. They are shown here. What were our experiments? We have tested 2 lexicon-based methods of sentiment analysis adapted for the Russian language, Sokal and Sensi strength, as well as a deep neural network model, RuBERT. We have run 2 series of experiments. Two series of experiments. In the first series, the training data were used to select the optimal hyperparameters for lexicon-based methods, lexicon and threshold values. And we also fine-tuned RuBERT. In the second series, the lexicon-based methods with selected hyperparameters were compared on test data with the fine-tuned RuBERT model. For all the corpora, a 3-class problem of sentiment analysis was solved, the classification of text into positive, negative, and neutral. We used the macro F1 score as the main performance metric. In general, lexicon-based methods can be used for sentiment analysis without training. However, since our training corpora are available in our experiments, we have used them to tune the hyperparameters of the lexicon-based methods. We have chosen the optimal sentiment lexicon for both methods out of 17 lexicons, and have determined the thresholds for positive and negative sentiment classes. The thresholds were defined as follows. Sokal returns the single sentiments for S for the text to be converted to a class label, positive, negative, and neutral. We have fit 2 thresholds, T, neg, and T pos, to divide the result to 3 variants, negative, neutral, and positive. Senti strength results is shown here. Senti strength results 2 scores, positive S pos and negative S neg. We select 2 coefficients, K newt and K, in such a way shown here. The results of selecting the optimal sentiment lexicon are shown in this figure. Kotelnikov's lexicon turned out to be the best for SoCal, and Lex 1 and 2 turned out to be the best for center strength, and we decided to take Lex 2 as it is smaller. The mean values and standard deviation of the fitted thresholds for SoCal with Kotelnikov's lexicon and for center strength with Lex 2 are shown on this slide. The pre-trained RuleBird model was fine-tuned separately on each training corpus with the following hyperparameters shown here. The results are given on average for 5 runs to reduce the influence of random weight initialization. The training has been carried out using the Google Colab Pro service on NVIDIA Tesla P100 and V100 video cards. Averaged results on all the corpora are the following. RuleBird is superior to lexicon-based methods on average over all the corpora. The results of the comparison of lexicon-based methods with RuleBird on each corpus are shown here. For 12 corpora out of 16, RuleBird, it's green, outperforms both lexicon-based methods. For most significant, the most significant difference was for example, Rule Sentiment, Century Eval 2015 Banks, and REMIP 2012 News. However, for 4 corpora out of 16, SoCal comes out on top, and for 3 of them, the difference is quite significant. You can see it here. There, for example, Century Eval 2015 Cars, Semi-Eval 2016, Century Eval 2015 Restaurants, and also REMIP 2012 Books. It's here. Center strength, as a rule, loses to both methods, with the exception only, which is here, for Century Eval 2015 Cars. We analyzed the length of the text. It's shown in yellow color here. In general, RuleBird analyzes all the corpora with short texts much better. An average number of symbols in the text less than 100. For medium-sized texts, the lexicon-based methods are better, and for longer text, RuleBird is the best again. Now let's move to discussion. We have compared sets of predictions on all the test corpora for all the methods. We have calculated the macro F1 score for each of such 5 subsets shown here. And what did we find out? The table shows that for the set of matching predictions, where every methods have the same answer, the performance turns out to be quite high. On average, these are shorter text. For the set of matching predictions from RuleBird and SoCal, it's here, the third row, 18% of the test data set. The result is significantly higher than that of the center strength, which didn't coincide with them. For the set of identical predictions from RuleBird and center strength, the fourth row, 17% of test data set. The difference is smaller. Center strength is worse than SoCal. Finally, for the set of the unmatched predictions, the fifth row, 6% of test data set, RuleBird is far superior than both lexicon-based methods. We analyzed in more details the situation when lexicon-based methods have the same answer and RuleBird has another answer. The results of lexicon-based methods were significantly lower than for RuleBird. In this case, lexicon-based methods poorly recognize positive and negative texts in comparison with RuleBird, but for neutral texts, the difference is not so significant. We also analyzed the reasons for the incorrect predictions of the lexicon-based methods. Errors most often arise due to an insufficient size of sentiment lexicon, the absence of sentiment words in the text, an incorrect recognition of negation and irrealis, an overbalance of words of the opposite sentiment, sarcasm and erroneous identification of domain-oriented words. As an illustration, we can give some examples that are incorrectly classified by the methods. The first and the third row examples are incorrectly classified by lexicon-based methods, and the second and the fourth are misclassified by RuBird. The first column shows real class and the answers of the methods. The second column is in Russian. The third one, translation into English. Sentiment words and examples are colored. Positive ones are green and negative ones are red. In the first example, lexicon-based methods didn't recognize that the phrase certain troubled debts has positive polarity. In the third example, the word wonder led the lexicon-based methods to their own decision. They didn't take into account that the phrase ATMs do not work is negative. Unfortunately, RuBird doesn't have the same good interpretability as lexicon-based methods, so we can't explain why RuBird misclassified the second and the fourth examples. But as we can see from the first and the third example, RuBird can correctly classify texts even when they have words of opposite sentiment. So, the conclusion. We have compared the lexicon-based methods SOCAL and Centistrength with a deep neural network model RuBird on 16 Russian language sentiment corpora for 3-class problem of sentiment analysis. On average, RuBird shows a higher classification performance than lexicon-based methods, exceeding SOCAL by an average of 5 percentage points. Centistrength lags behind SOCAL by 10 percentage points. However, for 4 corpora out of 16, usually with medium-length texts, SOCAL shows better results than RuBird. This keeps us optimistic about the lexicon-based approach in general. In the future, we intend to modify SOCAL in order to more accurately take into account the peculiarities of the Russian language, such as negations and irrealis. Also, a promising area of research is the development of hybrid models that combine the ability to take into account the context of deep neural networks and linguistic knowledge contained in the sentiment lexicons. Here are some main references we used, and I want to thank you for your attention. If you have any questions, you are welcome. I don't hear you. No. I see you and understand.
Can you hear us now?
Yeah, now I hear you.
Yeah, so let's applause a little bit more for a speaker.
Thank you.
So we have time for one quick question. If you have a question, you can unmute yourself or write it down in a Zoom chat. I have one very short question. I don't know how you usually train BERT for sentiment analysis. Do you have to train it on user reviews, for example? Because as far as I know, RuBird trained on general domain data, not social media, not user reviews, and it could be some bias on news site. For example, in user reviews, you can describe film with some bad events, and it actually doesn't mean negative way. So is there any bias in BERT, and how you can deal with that, if you can say something on it?
Yes, thank you. Certainly you are right. there are such problems with RuBERT, and we fine-tuned it with the corpus of the same kind as we tested it on. So I hope that it a little bit helped. But you see, the results are not so high even for BERT. The mistakes are quite often.
Yeah, thank you. And there's 2 questions in the Zoom chat. Could you please comment on it?
Now, if possible, a question, what do you think?
Yeah, I can. Yes, please read it aloud and then provide answer if it's possible.
Okay, if possible, a question, what do you think, why might RuBERT perform worse on these 2 data sets? One of the main reasons was named by you now. It's the fact that a lot of words have many meanings, and RuBERT doesn't understand what meaning is now. It's the problem of Russian language. And besides, there are many, for example, reviews which are quite long, but the real sentiment is shown in a little part of the review. And the most part of the review is has a lot of lexica of another sentiment. And this can be another reason. And certainly sarcasm and other.
Thank you. And we have one more question, I guess, from Alexei Sorokin. Alexei, if you can please unmute yourself or just write it down.
I have just wrote down it in the chat, but maybe I can read it out.
Yeah.
So I think so in 2021. Okay, in I think that.
I've read it. I don't hear you now.
Can you hear me?
Now, yes, I hear you.
Okay, so the question is that there are methods that work that on small data sets work better than simple fine-tuning. Some like pattern designing, like p-tuning, and so on. And most of the sentiment data sets are rather small, so maybe BERT has just overfitted. Also, RuBERT is rather old, and now we have much better transformers for Russian, like RuRaberta, RuT5, and so on. And did you compare this against rule-based methods?
Thank you for the question, but no, we haven't compared them. We just use RuBERT with fine-tuning. Maybe
Because
we'll
it seems
later.
Thank you for the answer, but it seems to me that you use both rule-based methods and BERT not in rather imperfect setting, because in Russian, to properly detect the scope of the negation, morphology is not enough. You need syntax, and you don't have syntactic annotation. And also among the transformers are available for Russian, RuBERT is not the best option. So I think the results for both kinds of methods can be improved, but maybe I'm wrong.
I can't say who is right, who is wrong. Maybe you're right, certainly.
Okay, thank you for your question, and we have one more announcement.
Just a quick note, comment that the topic of sentiment analysis will be continued tomorrow in the invited talk by Jeremy Barnes. So make sure not to miss it. And this probably will be of great interest for the authors of the current talk. So just stay tuned.
Okay, let's thank the speaker again. And
thank you.
Now we have 10
Goodbye.
minutes break for a coffee. Hi everyone, we would like to start the second NLP session with a talk from Yana Shishkina and Olga Leshevskaya. Please go ahead, the floor is yours.
Thank you so much. Can you hear me? Okay, today we're gonna present Belarusian Universal Dependencies Tree Bank. We work in a kind of, well, very popular framework, which is called Universal Dependencies. And this is a way to unify notation among different tree banks for different languages. And at the moment, more than 120 training languages have data annotated in this schema. And some of the data also have an additional layer of annotation, which is called enhanced universal dependencies. Actually, the motivation for our research was that Belarusian tree bank was annotated only with basic dependency trees. This means that each token has one and only one syntactic parent. And well, enhanced dependencies is a graph atop of basic dependency trees that allows one to handle additional deeper and richer semantically motivated relations between tokens, including coreference, coordination, argument sharing, and things like that. So we decided to add enhanced annotation to Belarusian universal dependencies using existing tree banks of closely related languages, namely Russian and Ukrainian. The agenda for today's talk are how we developed rules, then did some transfer using existing models for Russian and Ukrainian and doing some alignment. And then we trained a model, and then we just we are going to present an analysis of our results. Okay, so just very briefly, I will present some language-specific features for East Slavic languages. Actually, these languages are very closely related, and they have similar word order and similar syntactic structures and similar morphology. But the difference is in some details. And here you see an example of the phrase "Здравствуйте", "День добрый", or "Доброго дня". And you can see that actually, even though Russian, Ukrainian, and Belarusian are closely related and genetically related and have a lot of context-induced features, there are some other additional features borrowed, for example, from South Slavic languages such as "Здравствуйте", or from contacts with Polish and the history of Belarusian and Ukrainian as part of Polish-Lithuanian Commonwealth. Some language-specific constructions include constructions with participles. Belarusian lack, for example, present passive participle. And here you can see an example when there is a participle in Russian, but light verb construction in Belarusian and Ukrainian. As for the government, in some cases, the constructions are just similar, but in many cases, Belarusian uses prepositional groups, and Russian and Ukrainian use just case constructions. And as for comparative constructions, in some cases, we can use very parallel constructions, but
in constructions like чаще других, more often than others. You can see an example when we have the use, we see the use of the preposition in Belarusian and Ukrainian, and just case, genitive case in Russian. Oops, no. No. Okay, so what, for those who are not acquainted with enhanced dependencies, they were introduced in Manning and Schuster paper of 2016. And actually, there are 5 most major ideas here. First, to propagate dependencies to all of the coordinate tokens or constructions. To annotate coordination construction. Second one, to add relations between controlled verb and its semantic subjects and objects, and in general handle control and rising in the languages. Then there are annotation with regard to the information about case, prepositions, and conjunctions, some relations. And we can also annotate, move a relation from the conjunction in the relative clause to its referent. And to see what kind of lexical stuff is behind the relative clause construction. And the fifth idea is to handle ellipses and to restore elided nodes. Okay. So here you can see an example of some additional links in the enhanced representation, which is you can see in red. And here you can see that we add additional subject relation. We add additional relation between people and plant and such, and do things like that. So as for related research, I've already mentioned Schuster and Manning paper about enhanced universal dependencies. And then we actually were motivated by the IWPT shared task of 2020 and 2021, in which various models for parsing enhanced dependencies were introduced, and actually data for Russian, Ukrainian, Polish, Czech, and many other languages were created and corrected for this particular shared task. And another sort of source of motivation was papers by Tyers et al. 2018, who used methods of cross-lingual parsing to create 3 banks for Scandinavian languages. But their idea was applied, their method was, this method was applied to the basic trees. And Agic and et al. 2014, they served methods for cross-lingual parsing for West and South Slavic languages. Okay, data. So Belarusian corpus was created in the High School of Economics, and Nikita Login, who presented his talk today in the morning, was in the first team who annotated Belarusian data. And we started from the parallel Russian and Belarusian data, and actually propagated relations from Russian to Belarusian. After which, using the smaller tree bank, we started to train UDPipe models for Belarusian and then just correct our data manually. And Russian syntagrous data have an existing corpus, Russian syntagrous, with its original framework of dependency annotation. And these data were actually converted from original annotation to universal dependencies. And you can see that the variety of genres is a bit different, but well, all corpora actually try to be representative and to include various genres. And as for Ukrainian IU, this is the smallest tree bank in our collection. It contains also a variety of functional and law and social networks text. And it was also originally annotated in UD format, but the source of their annotation was mostly Polish tree bank. Okay,
so we can divide our research in three main parts. Firstly, we needed to develop some rules so we could annotate our data in a simple and quick way. So we would have some data to analyze the next experiments and to evaluate them. The next step is transfer the dependencies using the annotation from Russian and Ukrainian tree banks. And then we also trained a model on the Belarusian data, which was annotated with the rules. And the second part is the main part of our research, and it can be divided in three steps also. Firstly, we needed to translate Belarusian sentences into Russian and Ukrainian. Then we automatically annotate them, add enhanced dependencies, and then we align these sentences to project the dependencies. There are some details of the transfer method. We used Yandex Translate to translate the sentences because we tried Google Translate, and it tends to significantly change the syntactic structure of the sentence, change the word order, which makes the alignment process more complex. And Apertium can handle out of the vocabulary words, so it is not useful for us. Then for annotation of these translated sentences, we used the model which was proposed by Alibaba NLP as the IVPT shared task of the previous year, and it showed one of the best results. For alignment, we used cosine similarity of the vector representations of these sentences. We extracted them from MBERT model, which is a contextual and multilingual model. Also, we use some additional rules. It's clear that we cannot project, for example, information about preposition from the other language, so we added them with rules. Also, we fixed some obvious errors. For example, we added the root if there was no root in the sentence at all. After that, we also trained a model of Alibaba NLP on Belarusian data. It didn't need any changes in the construction of the model, so we didn't, there is nothing to explain too much. So here you can see the results. Usually for evaluating the enhanced dependencies, they use enhanced label attachment score, which is a F1 score over all of the arcs and all of the labels. EULAS is the same, but it only considers the labels which are universal for all of the languages. So as you can see, Belarusian model performed a little better, and Ukrainian and Russian transfers gave almost the same results. Let's us move on to an analysis of this data, and we will analyze all of the methods used in this study. And these are some examples of the differences which occurred after the transfer. First example shows that after the transfer method, modifier words tend to have one specific relation, which adds the relation between the head of its head. It's a little hard to explain, so it's better to see on the picture. And we don't completely understand why it's important to add this. So it wasn't in our rules. The next picture shows that our rules are not always more precise than the model, than the transfer. For example, in this case, transfer performed better at finding the semantic subject of the control verb. Also, the differences between language annotations often occur because of the differences in the languages. And for example, the inventory of the bound expressions in the languages can differ. So as you can see in the field is a bound expression for Belarusian, but it is not in Russian. And also one of the special features of Ukrainian trepank is that participles in Ukrainian are thought to be adjectives and not verbs as in Russian and Belarusian. So it changes the relations too, because according to the universal dependencies rules, adjectives can be adjectival modifiers, of course. Let's move on to the alignment method. Here you can see the confusion matrix of the phrase "I love cats" and "cats love me." And it's clear that if a sentence have more than one similar word, it's easy to confuse them when aligning, because they will have a high cosine similarity. But this sentence actually presents that the problem goes further, because maybe in English there are a lot of similar words, like the same words, but in Russian and in Belarusian, they're all in the different forms. So it's not only for like the same word, maybe for different forms too. And also it can use some bound, but just two words which used together often. For example, Republic Belarus. These two words can confuse because they always used together. Let's analyze the results of the Belarusian model. These constructions with nominal clauses are difficult to annotate even by the human hours. So of course, for the model, it would be difficult too to understand where is the subject and where is the predicate. And it's important to note that this problem doesn't only occur in Belarusian model. Of course, these mistakes can occur and in transfer, because the same model is used for the transfer too, not just the same structure of the model. Also, in some cases, it's necessary to understand the whole semantics of the sentences. And it's easier to do when you're human and not the machine. And for example, here you can see that it shows different subject for the control word, and it's not right. But the model can be more precise sometimes. For example, it can find or predict the grammatical features of the words which do not have one in the annotation of the UD. For example, of abbreviations and some words that just do not change form. So we can conclude that although these three Slavic languages are very similar to each other, they differ in details, even in the universal dependencies, which goal is to be universal and have similar annotations. So if we consider these little details, we can improve our method of transfer or just annotation. And also, it's important to note that even though we cannot give exact numbers, which of the parts or steps of our research gave the most of the mistakes, we can say that alignment was not very successful. And if we use different methods, we can significantly improve the overall result. And the model based on originally trained on Belarusian data is better than just our transfer. Thank you.
Thank you, Yana and Olga. Like we're a little bit out of time. Only if you have small questions we can ask, or just there is no question in chat, so please write to Yana and Olga if you have any questions. We don't have. We have slides. Thank you. The next talk will be presented by Alexey Sorokin. Now we will. Alexey, could you please share slides? Okay, let's start.
Can you hear me? Обратный отсчет или можно начинать? Замечательно. So good afternoon to everybody. My name is Alexey Sorokin, and I'm very pleased to have an opportunity to present my work on morpheme segmentation and on using BERT embeddings for this task. So what is morpheme segmentation? As practically everybody knows from the middle school, it is a task of dividing the words into morphemes, say prefixes, roots, suffixes, endings, and so on. Sometimes the morphemes are also normalized. It makes sense in case of some phonetic phenomena, and it is rather common in Russian, but we don't touch this task in the current work. And sometimes we also annotate the morpheme types. That is the notation from Russian dataset of Sorokin and Kravtsova, where we annotated with prefixes, roots, suffixes, and some other minor categories. But in principle, you can have some other annotation scheme. So what are the applications? Before talking about some downstream application, I just would like to say that morpheme segmentation, as any linguistic task which can be performed by human, is worth to be automated, because well, any task that a human can perform in ideal should be performed by a machine, no matter is it playing chess or morpheme segmentation. So, but in computational linguistics, we need morpheme segmentation. Well, sometimes it is helpful for morphological parsing, because the morphemes correspond to the values of some morphological features, like case or number and so on. Also, when you translate from agglutinative languages, like Finnish or Turkish, you cannot consider the whole word as a unit. You need to divide it into small meaningful units like morphemes. But it was this statement was true before the using of transformer models that mostly use BPE tokenization. But nevertheless, during the last 2 years, there is quite a large number of works that demonstrate that convenient BP algorithms like sentence piece or word piece or any other, they are suboptimal for agglutinative languages. So we need better subword segmentation for better tokenization and for better downstream performance of big pre-trained transformers. And also morpheme segmentation is very important for doing field linguistics, for annotation, for lexicon construction, and so on. So well, what are the approaches? If we take into account the supervised approaches, which requires annotated data, one of the most successful classical approach was the conditional random fields of Rokalainen et al. And it was also extended to be semi-supervised by using the so-called Harris features. I will tell something about them later. There were also some neural models. I would like to mention like only the two. The first one was applied to some indigenous Mexican languages by Kwon and Magda, and it uses simple sequence-to-sequence model with attention. And it demonstrated suboptimal performance, but this model had rather interesting semi-supervised extension, which utilized autoencoding, which is the restoration of the original word as an auxiliary task. And the most successful approach for among neural methods, as I know, among those that I know about, was the convolutional neural networks. We can also extend them using the unsupervised task of character language modeling. It is something like Elmo architecture in the case of words. We train the model not only to perform the task under consideration, but also to predict the next and the previous character. So, but what's the problem with applying all this beautiful stuff? That most data sets for morpheme annotation, even for such high resource languages like English, there are of very small size. That's because morpheme segmentation was usually treated as a non-supervised task. Because when a human does morpheme segmentation, it usually doesn't take any labeled annotation into account. The human compares a word with some words that have similar meaning, and then the parts which differ between the two words are natural candidates to be morphemes. For example, we have in English the word trains and the word training, and we select the common part train, and also select the different parts s and ink, and treat all this as morphemes. But well, no matter that human does so human usually do morpheme segmentation in some unsupervised way. That's why there are not so much large morpheme segmentation data sets. The only two exceptions are the data sets of Sorokin and Kravtsova for Russian, and the recent data set of Volodina and her colleagues for Swedish. So traditionally, morpheme segmentation was treated as semi-supervised task. Among the most successful approaches, there were Morphessor, which imposes a joint probability model of a lexicon and word types and morpheme types, and then used something resembling the hidden Markov models. And the recent work of Gromrose and his colleagues shows that Morphessor is closely related to sentence piece word segmentation. And since what sentence piece usually doesn't sentence piece isn't designed to produce morpheme sequences, it means that Morphessor is suboptimal because it resembles something that has practically nothing to do with morphemes. So another more successful approach is adaptive grammars. They were developed by Johnson, and now there was an active work from Eskander and his colleagues. If we don't dive into details, adaptive grammars are a variant of probabilistic context-free grammars with some additional adaptive mechanisms. They have some they work generally better, much better than Morphessor, but well, the software for them is rather difficult to run. At least I wasn't able to do that, and the model was very slow to train. So We also have some semi-supervised approaches. I mentioned them earlier. So we have semi-supervised conditional random fields. We have semi-supervised sequence-to-sequence model with autoencoding, and we have semi-supervised convolutional model with character language models. But in modern linguistics, most tasks, mostly unlabeled data, is used using the big pre-trained language models. And a related task of word segmentation for Chinese, where we don't have space word bounds, is usually solved by fine-tuning something like Bert or Roberta or something even more powerful. But if we have small data sets, we cannot train transformers from scratch. They will overfit. Even we cannot fine-tune BERT because it will overfit also. Okay, in 2021, we know that we can do something like p-tuning and so on, which doesn't overfit so easily. But in the time of writing that paper, I was not aware of this modern method. So the only possibility to invoke BERT was to use its embeddings, its features. So, and it's, well, it looks promising because first of all, transformers use BPE tokenization, and BPE tokenization is closely related with co-occurrence statistics, which are of characters, which are closely related with morpheme boundary properties. And also BERT embeddings represent semantics. And when a human does morpheme segmentation, it certainly utilizes semantics because it considers some semantically related words. So we treat morpheme segmentation as sequence labeling. That is the scheme. We use the beginning, ending, middle, and single tokens. Of course, sequence labeling can be easily extended to morpheme types, but we didn't have such a notation in our data. The basic feature extractor was taken from the work of Sorokin and Kravtsova, and it is the simple convolutional layer which we all know about. It's just applies windows of different sizes and extracts features from that windows using matrix multiplication. And we extend these features using BERT. So if we consider this particular position where my mouse is now on, we can consider all the spans which end in this position. I append these spans with the special symbols that BERT use for its tokenization for non-word initial segments. So we consider the spans that are from the left of the current position and from the right. If some spans, we don't have a span of length 5 because the end of the word is much closer, so we just replace it by the vector of all zeros. If some of these subwords don't occur in BERT vocabulary, we also replace them by the vector of all zeros. All other segments are replaced by the embeddings in BERT embeddings layer. So we don't use BERT as a whole. We only use its subword embedding layer, and any other subword embeddings could be utilized for the similar purpose. But we cannot utilize, say, fast text due to some implementation details. Not our implementation, but due to details of official fast text implementation. So we extract all these subwords. This one means that we extract the longest subword that ends in the current position, which is repeated in this case. So we extract all such subwords, concatenate them, and then project it to low dimension. It, as I remember correctly, it was something like 256 in our experiment. So, and then we just pass on this through traditional convolutional network. And we, our model produces label probabilities, and we decode the most probable sequence using Viterbi decoding. So the results are on this slide. The results are positive. BERT outperforms the previous model, the previous state of the art, I think, almost for all languages. There are problems only for Georgian and Zulu, but these are the two languages which were not present in the training that didn't have language-specific BERT. Because for Estonian, Finnish, Turkish, and certainly English, we have language-specific BERT models. And for Georgian, we have only the multilingual, where Georgian is underrepresented. And for Zulu, we don't have even the multilingual model. And because Zulu uses the Latin script, its tokenization is, well, it is not connected with Zulu morpheme properties. It's connected with morphemes. It segments to morphemes for some other languages utilizing Latin script. So, well, it's our main result. Now we're going to the ablations. First, the natural question is, why do you improve? You have added more parameters. Maybe just your network is larger. Or maybe the subword vocabulary helps because the B dictionary of BERT contains a lot of morphemes. Or maybe the weights of lower BERT layer actually convey some morpheme-specific information. To answer this question, we replace the BERT weights by the random weights using the same vocabulary. And we observe that the model with random vectors usually work much worse than the model with the same tokenization, but with BERT weights. So there are not only, it is not only tokenization that matters, but also BERT conveys some morpheme-specific knowledge. But if BERT is so wonderful, why cannot we fine-tune it further on the task related to our specific task? For example, on morphological tagging, or on BERT nature, or on BERT mask language modeling, but not on the level of subtokens, but on the level of but on subword level. So we apply BERT mask language model to individual words. And also we can do word-to-vec like training, but train not word vectors, but subword vectors, and consider not sentences, but individual words. Well, the bad news are that practically nothing helps. Fine-tuning BERT deteriorates its performance. And if we consider the next slide, we can see that word-to-vec helps for languages where the original BERT model was rather weak, for Georgian and for Zulu. And for languages where the original BERT model was strong, it either performs on the par, like for Estonian, or is slightly better like for English, or is significantly lower, like for Finnish and Turkish. Why it happens? I hypothesize that for Finnish and Turkish, the original tokenization of Finnish and Turkish BERT was much better than the BP tokenization we were able to learn using the word list from the MorphoChallenge repository. So, what are the positive results? That BERT embeddings improve morpheme segmentation. The language-specific models, as expected, work better than multilingual models. And then word-to-vec training on some word prediction provides a cheaper alternative. What are the negative results? That we don't understand exactly why it happens and why it sometimes doesn't happen. And then and also that linguistically motivated fine-tunings and other linguistically motivated approaches doesn't help, don't help. For example, I tried to utilize the unlabeled data by enforcing the model to predict the same segmentation for the root of two forms of the same word. For example, I don't know the exact tokenization of trains and training, but it must be the same for the first 5 letters of this word, of this word. But this additional contrastive task doesn't help. So, what are the further ideas? First, to utilize BERT in some approaches that don't overfit so easily, like use adapter layers or use speed tuning or something like that. To explore subword information further, maybe by adding not only convolutional connections, but also some graph, but also to construct some graph with some words on its edges and apply some kind of graph neural network. Well, the most simple solution, I think, is simply to collect more data. Because, well, if we need morpheme segmentation for some industrial applications, it would be much faster to collect and annotate. Just say to parse dictionary, to fix the errors manually, and then, well, it is not a difficult task, I think. And also, can we design a better probabilistic model of unsupervised segmentation? Because Morphesser and sentence piece, they utilize only a unigram language model, in fact. And of course, a unigram language model can be replaced by something more complex that better reflects the inner structure of a word. But maybe it's the last idea, it's, well, I like it the most, but I think it requires much more deep dive into mathematics and into linguistic understanding of morpheme structure than the other approaches. So, well, thank you for attending my talk. You can find the code on the GitHub repository. You cannot find the whole data because some of the data sets is proprietary. And but for example, the Morpho challenge data, it is really available on the site of the challenge. So thank you for your attention.
Okay, can you hear us?
Yes.
Yeah, so let's thank the speaker again. Yeah, I see some messages in the chat. If anyone asked a question. Yeah, there's a question from Alexander. Alexei, could you please read it? And
yeah, Alexander. The question of Alexander is that we have an embedding of the size 12 times 768, which is the birth dimension for each letter, and then we project it to some lower dimension. Yes, it's exactly what happens in the model, because the convolutional layer uses the representations also of size several hundreds, and we have to project birth into the similar size.
Thank you. Does anyone have a question? Yeah, 1 second.
Can you hear me?
Yes.
Okay. Did you use, you mentioned you use CRF, but I believe hidden Markov model is suitable too. It's naturally unsupervised, and something on top of it. Did you try to use HMM, not CRF?
I didn't try it, but as far as I know, among the not Euro approaches, the CRF approach of Ruokolinen was better, at least according to the results of his paper. And because the code for it was freely available, I just ran this code using some minor modification. And I know that supervised Morfessor uses HMM, but Morfessor demonstrated much lower results, and I wasn't able to do something like hyperparameter tuning to make it work better. So the refs was more
it's
convenient.
inside Morfessor. Okay. It's actually inside Morfessor already.
I'm not sure whether I used the optimal version of Morfessor. I just picked some, and maybe the numbers in the paper for Morfessor may be slightly better, but I think not better than CRF.
Okay, thank you.
One more question?
Thanks for the talk. Just a small question, not actually exactly related to morpheme segmentation. Just a minor thing about, am I right that you trained this word-to-vec model on BP segmented tokens, right? On subwords?
Well, maybe I can show the slide again.
Yeah.
Okay. So I tried I tried two variants of word-to-vec training. In the first one, I used the original BERT vocabulary segmentation. And in the second one, I tried the DPE trained on the word list available for the languages. And the second variant is slightly better, I think, because the BERT vector size is much larger than traditional vector size for word-to-vec, which is 300. And I think the model overfits. So this lower variant with the BPE trained on the same corpus performed better.
Yeah, but essentially my question was very practical. Can I lay my hands on this model, because I really wanted for a long time to try a word-to-vec trained on BP subwords. So have you published the model?
Not yet. I will have a look if I can easily share the training code, because I didn't use nothing more like GenSim and simple sentence piece commands for learning the segmentation.
Yeah, that'd be nice. Thanks.
Thank you.
Okay, let's thank the speaker again. The next talk will be about my work, so we will change slides. Okay, let's start with my talk about adverse drug reaction classification across different drug names. My name is Elena Tutubalina, and this is a joint work with Ilsiara Alimova from Kazan Federal University. Since we're a little bit out of time, I will try to not give you a lot of details about it and give you just high level of our work idea and main research questions. Great. So small introduction. We're trying to focus on detection of adverse drug reaction because it's one of the main tasks of pharmacology, and this is actually about post-marketing of the drugs, because a lot of different events happens when drugs face market, and it's really drug reprofiling task. It's very important, and usually unstructured texts are very promising source to find information about adverse drug reactions. one great study which I would like to discuss with you before discussing my work is work from our co-authors, colleagues from UPenn University and group from Garcia Gonzalez. And they actually show that social media, it's available source to find adverse drug reaction. It has to be used and it has to be considered with addition to official drug resources channels. They analyze adverse drug events found in Twitter, and some of them found in FIRES. It's an official database where doctor can submit adverse drug reactions in US. And also they analyze drug information databases and compare 3 different channels of information across different drug groups. And they saw that actually a lot of patients discuss different things in Twitter if you compare it with official sources from doctors and from official drug discovery companies. And it's really a cool study, and it's I see the study as like a proof of concept that you have to analyze all information available right now in drug marketing, including social media, reports from doctors, reports from different companies, and so on and so on. And now I will discuss what we did in this study. Okay. So our research question, we're focusing about classification of text with adverse drug reactions. Mostly current work use supervised classifiers and evaluate those classifiers on one specific corpus. Usually this corpus contain information about one specific drug or a group of drugs which research group are most interested in. And we believe that it contains a lot of bias. And our research question, we're focusing on cross-domain evaluation. Is in-domain evaluation where you have train and test data from the same benchmark give you some significant overestimation of performance? And can we do something with that if we find out that it's very good performance, but when you do cross-evaluation, results are lower? So second question which we face is, can we at least somehow use raw reviews about different drugs without any manual annotation in order to improve cross-validation and cross-domain performance of some specific models? And in this study, we analyzed BERT models and also LSTM-based models to see if we can see similar patterns for both types of models or not. These slides also present some example which is actually adverse drug reaction in the text. You can see that there's a two phrase with the same entity, unable to sleep, but in the first example, it's actually not adverse drug reaction. He was unable to sleep last night because of a pain. It was not caused by a drug. So the same phrase do not represent adverse drug reactions, while in the second phrase, you see that it's become unable to walk without a cane, unable to sleep. It actually was marked as adverse drug reaction in one of the data set which we use. So you can just use dictionary-based approaches and see that some phrases for different drugs can represent different things. It could be indication or adverse drug reaction and so on and so on. Okay, let me switch slide. Which we do as our pipeline. So it's a supervised model. In first types of experiments, we have one corpora, we train model on this specific corpora and evaluate this model on source test set and target test sets from different corpora which represent different drug groups. And in the second types of experiments, we try to use some additional unlabeled data. We distantly label data with already trained model. Then we select the best reviews which we wanted to add in our train set with self-annotated labels. And then basically we will train the full classifier. It was a quite straightforward way without any uncertainty estimation step in order to see if we actually need to add more diverse information in our corpora and then train on it. So we use two annotated data. I will not give you a lot of details about it. It's both corpora annotated with user reviews. Annotators selected adverse drug reaction sentences from those corpora and entities. And one corpora has information about two drugs from different ATC group, and the second corpus called CITAR mostly has information about physiatric drugs, of which nice, and both corpora have enough data. So one of them from one group of drugs, another one from another. And what's about RA reviews? We collected a lot of data which is not unlabeled from site called askapatient.gov, and we use 3 different subsets of this corpora to see if it can benefit our cross-domain training. So the first subset is actually the full data set which we use. We annotated with already trained model on one corpora on another. The second subset is basically reviews with the lowest rating, because if patients are not satisfied with the drug, they give it the lowest rating. So adverse drug reactions should be found even in this text just because of a rating. And the third group, which we actually see as overkilling for this task, it's a group about specific target drugs. So we know which targets we see in our test set, and then we select specific annotated reviews about those drugs. Which model do we use? We use LSTM-based interactive attention network and BERT. You all know about BERT, but probably not all of you know about interactive attention network. It's a network which was proposed 4 years ago for sentiment analysis. Basically, it's used see text as a context and entity embeddings, and then use cross attention between those two vectora and predict the class label on it. Our results. So here's our results on the first corpora called KADEC. It's a HISTA set, and you can see 5 different models. You can see that if you have enough trained data in one domain, you have a quite good macro F1 score. But if you have different domain or different drug groups, your performance will be much lower for both models, which is actually expected in NLP community. When you have different domain, different target group, you have much lower scores and significantly lower scores. But if you add some, even if you had more data, more diverse data about different drug groups in the market, even with pseudo-annotated labels, sometimes you can improve your performance. So for me, our findings give an idea that if you want to use models on diverse group of drugs, at least do something with your trained data. Even if it's pseudo-annotated data, it still will be quite good. And the second slide about results give similar things. We have CITAR test set. If you train on the same corpus, it's a cross-validation, but reviews about the same group of drug, you'll have significantly higher results when you train on different group of drugs. And then if you add more pseudo-annotated data, sometimes you can improve your scores, but depending on the subset. But for both experiments, results show that you can just add reviews with lowest rating, because it's when people do not satisfy with results, with the outcome of the treatment, and a lot of them are expressing adverse drug reactions. So, short summary, we studied cross-domain adverse drug reaction classification from user text about different groups of drugs, applied to different groups of models, see great drop in performance if you compare it with in-domain and cross-domain results. Automatically annotated data helps in most experiments, so if you can argument your data or pseudo-annotate your data, please do it. And we believe that future work can be focused on advanced NLP when you have adaptive self-training or meta-learning techniques to improve your collection. Thank you. If you have any questions, please ask. All right, in a Zoom chat. I think, oh, cool. We're now not out of time. Yeah, finally.
Yeah, thank you so much for your talk. I was wondering, what's your estimation, you know, when talking about the pseudo-labeled data, like by what amount of data that we have for training, it's okay to say, well, that's not enough, let's take pseudo-annotated data. So where is that, you know, when should we add more data with that way?
Yeah, thank you for your question. It's a really good research topic on how much actually annotated data do you need to train your supervised models. We did different experiments for different tasks related to adverse drug reaction mining from reviews, and sometimes it's not about how much data you need. Sometimes you need like 500 reviews, even if you have 3,000 of them. It depends on the task and also about drug rooms. So for example, for name entity recognition, you need like 30% of a really big corpora, like 100 over 300 or even 500. So 100, well, something like that. It would be enough, but it actually depends on the domain. For example, we did experiments when you try to find named entities about adverse drug reaction on social media or on electronic health records. Depending on the domains, this number will change, but it's actually, you don't need enough data to train your models. There is our paper from European Conference on Information Retrieval last year, I believe, where we published our results on how much data you need to train your named entity recognition model. And I can share a link with you, but it is what it is. Sometimes it's not about the number of annotated data, it's more about on which domain you annotate your data on, about which target drug target you're trying to use for evaluation and training and so on and so on. There are different characteristics that you have to consider, not just a number of annotation itself. Okay, so let's continue with the second talk. The next talk will be about morphological model presented by Elena Bolshakova and Alexander Sapin.
Yeah, can you hear me?
Alexander, could you please share slides? And
Yeah. Okay. Can you see the slides?
Yeah, we can.
Oh, awesome.
Yeah, you have 25 minutes.
Okay, nice.
Please.
Hello, my name is Alexander Sapin, and today I'm going to tell about combined morphological model which produces both morphological tags and morphemic segmentation for Russian word forms. Morphological analysis is a basic stage of natural language processing, and there are several tasks related to morphological analysis. Some of them are quite traditional, like lemmatization, morphological tagging, and the most complex task, disintegration. And there are also another task which is also related to morphological analysis, which is called morphemic parsing or morphemic segmentation. And this task can be solved in different variants. The most simple variant is pure morphemic segmentation, when we need just split words into morphem-like units. And another variant is morphological segmentation with classification, when you need not only split words into morphs, but also assign labels for each morph. And of course, for languages with rich morphologies, both inflectional and inflectional tasks and morphemic parsing are much more complex because we have very complex word formation, we have a lot of different suffixes and so on. There are two main approaches for traditional inflectional morphological analysis. The first is dictionary-based approach, where morphological dictionaries with word forms or stems are used, and lemmatization and morphological tagging in this case is quite simple. It is just a dictionary lookup, but these approaches require additional procedures for handling of out of vocabulary words and for obviously for morphological disambiguation. But dictionary-based approaches are quite fast, so they widely used in morphological processors for Russian language. Another approach is pure machine learning-based approach, and this approach relies on word embeddings and sometimes allows to get rid of morphological dictionary at all. And the most quality achieved by approach based on machine learning, both for morphological tagging and lemmatization. But the main disadvantage of such models is that they have quite low performance compared to dictionary models, to dictionary-based approaches. So, and we already had a very good introduction about morphemic parsing from Alekseev. I'll just cover it in a few words. We have two approaches for morphemic parsing. We have unsupervised approach, and the most known system-based unsupervised method is Marquesov system, but such approach doesn't show good quality for morphemic segmentation, and it was used mostly because, as Alexei said, there was no data sets of sufficient size. And the first data set which appeared for Russian language was based on Tikhonov's dictionary of Sorokin-Kravtsova data set with 96,000 of segmented lemmas or Russian lemmas with classes of segmented nodes. And because this data set appeared, several supervised approaches were proposed. They were used different machine learning methods, convolutional neural networks, gradient boosted trees, long short-term memory, but they all show quite comparable accuracy, about 85 to 89% of fully correctly parsed words. But these numbers are quite high, but all these models have a big disadvantage. They trained on the data set which contains only lemmas. So you can just take these models and apply them to text because text consists of word forms. So we decided that we need to solve this task for word forms, and first of all, we need to create a data set which contains segmented word forms, and we created such data set, but it was a hard way. We tried 2 times. First time, we tried to create rule-based procedure, which will produce segmentation of word forms based on segmentation of lemmas, but very fast it became clear that it is almost impossible. So on the second try, we used inflectional classes of Russian language and created data set which is freely available. It is called Rumor's words, and it contains more than 2 million segmented word forms, Russian word forms. Also, we trained a model on this data set, and this model showed quite good accuracy both for word forms, and what was surprising for us is this model showed better quality for lemmas than models which were trained only on lemmas. But it's a good result, but the main disadvantage of this model, and actually it is not a disadvantage of this model, it's a feature of this task. When you need to perform morphemic parsing of word forms, you need to know, in some cases, you need to know part of speech. Because sometimes in Russian language, morphemic segmentation depends on a speech part, and you can see an example of the slide for the word Maia. So we decided that it is reasonable to develop a combined model which
produces both morphological types and segmented word forms and doesn't depend on external morphological analyzer, which will detect the speech part, which will disambiguate it, and so on. So another motivation for this combined model was the idea that obviously these inflectional tasks and morphemic parsing are related tasks. So morphology is unified language mechanism, and in some NLP applications may require both morphological text and morphemic parsing. So we decided to develop a neural network for inflectional morphological analysis, actually morphological tagging, and morphemic parsing. We decided that we want to train a fast model, so we use convolutional neural networks and both morphological and morphemic features. But of course, there are two challenges. First of all, we have to develop architecture of such model, and it will be not so trivial as, for example, model for more form segmentation or lemma segmentation. And also, we need a corpus because we want to use both morphological and morphemic features. We need a corpus with both morphological text and segmented word forms. So we solve both challenges in some way. We solve both tasks as classification tasks. For morphemic segmentation, this classification, we classified each letter of each word to 10 classes. And for morphological tagging, we also use different set of classes for partial speech tagging, for cases, and so on. Our model process text by fixed sequences of 9 word forms, each of up to 20 letters. As morphological features, we use fast text embeddings and variants of morphological text from dictionary. And obviously, it is not the best possible way. If you want to build the best morphological tagger, it is better to use BERT embeddings. Even frozen BERT will show much better results than this combination. But we wanted to have a quite fast model, so we used these features. And of course, for morphemic segmentation, we used one-hot encoded letters and the variety of each word form. And on the next slide, I'll show the architecture of this combined model. But in general, it consists of 2 parts. We call them submodels. One of them responsible for disintegration, and another implementing morpheme segmentation. And they are very similar. Actually, you can see architecture of combined model in the slide. As I said, it is based on convolutional neural networks, one-dimensional convolutional neural networks. The basic building block of the model is convolutional block, which consists of a one-dimensional convolutional layer, dropout, and max pooling for faster training and evaluation. And in each submodel, we use 3 such convolutional blocks. So you can see an example on the slide. We have a part of sentence. We encode it with our features, so we produce vectors from fast text and variants of morphological text in dictionary. We pass them to convolutional blocks, and after that we have classifiers for different morphological text. And of course, we need also solve morphemic parsing test. So we use one-hot encoded letters and output of classification layer for part of speech as input to convolutional blocks of morphemic segmentation. And after it, we also have fully connected classifiers, which produces classes for each letter. And the same details on the slide. We use 3 convolutional blocks with different number of units. We use fully connected layers and output of part of speech fully connected layer connected with morpheme submodel. Okay, architecture problem is solved somehow. So another problem is dataset. And obviously, dataset with both morphological and morphemic labels don't exist. So, and creating such dataset from scratch is a very complex and almost impossible task. So we decided to use Syntagrous as a source for our dataset with both morphological text and morphemic segmentation. And as I said before, we have a model which can produce Markov segmentation for word forms. So we just added automatically Markov segmentation for word forms from syntagmus. Of course, we had some post-processing, some exception, some rules for short words, for non-Cyrillic words, for numbers, and so on. But in general, this Markov segmentation was produced automatically. And of course, this data set contains some errors, but it's okay for our experiments. Okay, we trained our model on this data set. We divided it into 3 parts for training, validation, and testing, and evaluation results was the following. We get about 94.2% of accuracy for morphological text, and actually this number is not comparable with the best results which I showed on the slide, because they were achieved for for a large collection of different texts, but this result is acceptable for our task. Also, we received very good results for rumor syntax rules for Markov segmentation, for Markov parsing, more than 96%. And these results actually look very suspicious. So it is too high. So we additionally evaluated this model on rumor's words. And we found more than 2 times worse quality of Markov parsing. So obviously our model overfitted on rumor syntax rules, and we are not sure why, but mostly because rumor syntax rules have very low Markov diversity. Because this text, there are a limited number of different words, a large number of short words, and many words similar in structure. So to overcome this problem, we divided our training into 3 stages. On the first stage, we trained our Markov submodel separately on a data set with word forms, which is called rumor's words. After that, we freeze weights in Markov submodel and train combined model on rumor's syntax. After that, we unfreeze all weights in our model, lower learning rate up to, I think, 2 orders, as far as I remember, 2 orders of magnitude, and have a fixed number of iterations, and trained our combined model again. So the results was the following. Accuracy for morphological text was the same, it's okay, and accuracy for Markov parsing was quite good. We have 88% for rumor's syntax rules and 91% for rumor's words. So actually, we tuned a number of iterations and learning rates on the 3rd stage, and find that we can improve quality for rumor's syntax rules and have worse quality for rumor's words, but we think that these parameters are optimal. Also, we evaluated, we analyzed errors of our model, and of course, we found that rumor's syntax rules contains some errors, but more often our model produced errors in Markov segmentation. And of course, the most popular error type for Russian language is errors on boundary between root and suffix. Also, there are errors between prefixes and roots and endings of words. And you can see statistics of error on the slide. The most popular errors are between root and affixes or sequential suffixes. Okay, and we developed a combined model which shows comparable with best quality of Markov parsing and word level accuracy, and acceptable quality of for disintegration of morphological text. We developed necessary data set. Of course, this data set contains errors, and we have to improve it, to manually improve some errors, to manually fix some errors. And also, the developed model have acceptable performance. It shows about 2,000 words per second in a single core mode on an ordinary CPU, and have a relatively small size. And but probably we have to consider a different architecture, maybe use fast text segmentation, because fast text has internal segmentation of word forms, maybe use it as a feature for Martinez submodel. Maybe we can improve quality and even performance in some way for our model. So that's all. Thank you for your attention, and I'm ready to answer questions. For some reason, I cannot hear it.
No.
Oh, I hear.
Alex, do you hear us?
Yeah,
now?
I hear.
Oh, okay, let's thank you speaker again, because first time we were mute. Is there any question? Okay, there's one.
Yes, thanks for the talk. Maybe I misunderstood, but am I right that this room of words syntagros dataset? Yeah, can you show the last slide, please?
Okay. Yes.
Yeah. So am I right that this room morphs syntagros dataset that it is not manually corrected for errors, so it was actually created automatically, right?
Yes, it is right. There were some errors were corrected, but they were also corrected automatically if I found some patterns.
Yeah.
I had some rules, but yes, no manual correction. Yes, it contains.
Yeah, which means that it cannot be like used as a full-fledged test set, right?
Yes.
All right, so that's something for the future work, I guess.
Yeah.
Is there more questions from the audience? Okay, let's thank the speaker again.
Thank you.
And now we have the next talk on Zoom, I guess. Let me see. Marco, could you please share slides?
Hello.
Hello.
Okay. Can you see the slides?
Yeah, okay.
Sound is good?
Yeah, we can. It's great. Yeah,
Awesome.
let's start. Thank you.
Good evening. I'm Matej Ulczak, and I will present our work training dataset and dictionary sizes matter in BERT models, the case of Baltic languages, which was done together with Marko Robnik-Shikonia, and we're both from University of Ljubljana. So some short outline. We have heard a lot about large pre-trained masked language models such as BERT today already. But we will present a bit more on the situation for Estonian, Latvian, and Lithuanian. And then our evaluation and comparison of models for these languages. And we will conclude with a summary of our findings and any further work on this topic. So large pre-trained masked language models such as BERT have become state-of-the-art for many NLP problems. However, they have a few problems such as the high computing resource requirements, which can be much easier dealt with lately than perhaps 2 or 3 years ago. However, another problem is the large corpora needed, which is especially problematic for smaller languages with fewer resources and not as many speakers. So massively multilingual models, yes, they cover these languages as well, but they're not enough. We have seen today already that they're not performing quite as well. And we might not have enough data to train a monolingual models for these languages, or at least not good models. So what we can do is perhaps train multilingual models which cover only a few languages to bridge this gap between large, massively multilingual models and monolingual models. So for Estonian, Latvian, and Lithuanian, the following models exist. So massively multilingual models trained on 100 or more languages, such as multilingual BERT and XLMR. Then for each of these languages, there is a monolingual model as well. For Estonian, AIST BERT, for Latvian, LV BERT, and for Lithuanian, LitBERTA. And there is also a trilingual model, Finest BERT, trained on Finnish, Estonian, and English. And we have now trained and released two new language models. For Estonian, a monolingual AIST Roberta, which is trained on much larger corpora than AIST BERT. And for Lithuanian and Latvian, we trained a trilingual model similar to Finest BERT. We called it LitLat BERT, which was trained on Lithuanian, Latvian, and English as well. The motivation for these two models, so let's first look at Estonian Roberta. As I mentioned, it is a monolingual Estonian model trained on larger corpora than Estonian BERT, which was underperforming on some tasks compared to multilingual models. And the corpora used to train these new AIST Roberta was mostly news articles, but we also used some web crawl data. It uses the same architecture as BERT-based or Roberta-based architecture, so 12 transformer layers. We did not use the next sentence prediction task, and we did use whole word masking. And the training took about 3 weeks using 4 GPUs. And for LitLat BERT, this was a trilingual model trained on 3 languages. And the existing LV BERT and LitBERTA were underperforming on many tasks. And compared to multilingual models, as we will see in the following slides. And the idea is that our corpora, which we used, which is mostly web crawl, but we also used some news articles and general language corpora, is not quite as large as would be needed for a good monolingual model, because it is comparable in size to existing LV-BERT and LitBERTA. But by combining these two together and also adding some English, which is not much larger than for Lithuanian and Latvian corpora, it is comparable in size to those two. The combined size for these 3 languages, the corpora from these 3 languages is much larger. So we can hope to train a much better model. And at the same time, we're focusing only on few languages, not 100 at the same time. So each of these 3 languages will be better modeled. And also what we can hope is to use this model for cross-lingual knowledge transfer. So for example, to train some or to fine tune on English for some end task and then use it on Lithuanian or Latvian. And the architecture used here is the same for us for Estonian Roberta model. And the training here took much longer because of the larger corpora, and it took about 2 months. Here we compare some of the sizes of the corpora used to train all these models. And we estimated some values because they are not explicitly given anywhere publicly. And what we can see is that multilingual BERT really used very little data for Estonian, Latvian, and Lithuanian. However, XLMR uses a lot of data for these languages, which is comparable or even larger than for all the other monolingual or trilingual models. As mentioned before, Estonian BERT uses more Estonian data than the trilingual finest BERT, but our AIST Roberta uses even larger corpora. And for LitLat BERT, the amount of Latvian and Lithuanian data is comparable to XLMR and the two monolingual models. For dictionary sizes or vocabulary used, the monolingual models, of course, use much larger dictionaries. However, a special outlier here is the monolingual LitBERTA, which uses 128,000 token vocabulary, whereas most monolingual models are about around 40 to 50,000. For evaluation, we used 3 standard classification tasks, named entity recognition on 3 classes: person, location, and organization. And then part of speech tagging task, where we used a universal part of speech tags. And we also evaluated on dependency parsing task. We additionally evaluated the models on a word analogy task, which is usually used to evaluate non-contextual embeddings, static embeddings, such as word2vec or fast text. But we adapted it for use with BERT models so that we put these analogy pairs in a boilerplate sentence with limited context. We then masked one of these words, and we try to solve this task as a masked word prediction, so to predict the masked word. And here are the results for named entity recognition. What we can see is that most of the models perform relatively well. The exceptions are perhaps the monolingual LV-BERT and especially LitBERTA, which perform significantly worse because they were perhaps trained on too small corpora or perhaps some other issue. Especially for LitBERTA, we are not sure because this model was never really presented anywhere or described in any detail. What we can see then is that multilingual models perform relatively well, but especially a good monolingual model will be better. So AIST Roberta slightly better than finest BERT, which performs better than, for example, Estonian BERT. And for Lithuanian and Latvian, our LitLat BERT performs the best. And perhaps one conclusion would be that large corpora is more important on this task than the amount of language-specific corpora, especially when you compare in Estonian that monolingual AIST-BERT performs worse than XLMR or finest BERT, even though it is trained on more Estonian data than finest BERT. Very similar results we can see for the part of speech tagging task, but here all models perform really well. But the relative performance between these models is the differences are really similar to the named entity recognition. Monolingual models perform slightly worse, and the performance gap to the best performing model is really small for massively multilingual models such as XLMR especially. But again, good trilingual models perform equally as good as a good monolingual model, and perhaps slightly better than a massively multilingual model, or roughly similar. Perhaps more surprising and more informative results are for the results on dependency parsing task. here we can see that massively multilingual models significantly underperform, especially MBERT, and that monolingual models perform much better. And it is here that corpora sizes are not really as important. What is important here is that the language is specifically modeled for one language, so it is language-specific model. However, these trilingual models can be somewhere around there, so much better than massively multilingual models, but not lagging much behind the good monolingual models. For example, on Latvian, the difference is relatively small, though Latvian monolingual bird performs the best. On Lithuanian, they perform on par, Lit-Lat-Bird and Lit-Berta. And for Estonian, the difference can be seen that already finest bird performs worse than AIST bird, but AIST Roberta, which is trained on more Estonian beta, performs even better. So, of course, much larger corpora used to train a model is always better for a monolingual model. But when there is not enough such monolingual data, then perhaps it is good to consider other options. And now the results for word analogy task. Here is, we were a bit surprised because our expectations were that multilingual models split words into too many tokens because they cover many languages, and that monolingual models will be much better here because first they have smaller vocabularies, so there are fewer tokens to choose from. And because they split the words into fewer tokens, especially some very common words will be kept together as a single token, it will be much easier to task to fill this mask, which will be, if it is only one mask to predict, it is much easier task than if there are three masks that need to be predicted. However, the results show that massively multilingual XLMR is actually the second best model for each of the languages, and that there is no clear advantage for monolingual models, with perhaps exception only for Estonian, but even then XLMR outperforms Estonian bird and finest bird, and finest bird outperforms Estonian bird as well. And especially Lit-Berta is severely underperforming, but this can be possibly explained because it had a really large vocabulary. And what we then did is looked a bit closer to vocabulary sizes. So we plotted on x-axis the vocabulary sizes for each of these models, and on y-axis the relative gap to the best model for each language. So the 0 will be the score of the best model here, and which is at the top, and then lower points on this graph will be worst performing models. And then we did the same for part-of-speech tagging, for dependency parsing, and for word analogy tasks. And there is no clear answer here, possibly because we also mixed monolingual and multilingual models here. But there are some trends which can be seen, especially that for monolingual models, increasing vocabulary sizes improves the performance up to a certain point. But then further increasing this size decreases the performance. The only exception to this is the dependency parsing task, where we don't see this drop of performance by increasing the vocabulary size. And for multilingual models, a similar thing can be observed, that larger vocabulary improves the performance. Perhaps it would be similar that further increasing would drop the performance, but we do not have any such models to compare. That would have much larger vocabulary sizes, so we could compare that. However, the results here are strongly correlated with the training data sizes. So to give the definitive answer, we would need to further study this, where we would jointly analyze vocabulary and dataset sizes but to do that, we would need to train separate models from scratch on exactly the same other parameters, same data, but that is very costly and it take a lot of time. So we leave that perhaps to future work. So to conclude this, we have released 2 new models for Estonian, Latvian, and Lithuanian. These are AIST, Roberta, and Littlead-Bird. And we have seen that they outperform existing models in most situations. And we have made them publicly available at Hugging Face as well as on Clarine networks. We have seen that larger corpora are beneficial for monolingual models. But when these corpora is sparse, when we do not have large enough corpora available, multilingual models which focus on few languages are the best solution, because there is some trade-off point where too little data, we have too little data to train a good enough monolingual model. But when we are past this point, then monolingual model can be the best performing model. But when we are below that, this is not the case. We cannot rely on monolingual models. These massively multilingual models covering 100 languages really cover too many languages to be good performing. So focusing on just 2, 3, or 4 languages is probably the best solution, especially when we have the ability to choose similar languages and especially related languages together as done for Latvian and Lithuanian. Ideal vocabulary size seems to exist, but it is language and the data specific, and perhaps even specific for each task and task. So it would be interesting to see this, a good full analysis of this, but as I have mentioned before, it would require training many models, and we leave that to future work. And with this, I conclude my presentation, and I'm open for any questions you might have. Thank you.
Okay, let's thank the speaker again. Thank you for the great talk. Do we have any questions in the audience? Okay, I guess, Andrey, you have to. Let's try.
Thanks. Thank you for the great talk. I have a couple of questions actually, but I probably will start with the first one. I was very much interested in you. Sorry, there's something going on with the camera, but well, I probably will survive. Yeah. So yeah, I was very much interested in your using word analogy task to evaluate contextualized language models. And yes, you're right that the vocabulary size plays a large role in the performance of your models, which indeed it seems are not like 100% comparable because of vocabulary sizes. Because am I right that you deemed correct or like fully accurate only the answers when the model predicted exactly the word which was masked, right? Not like the first subword of this word or something like that.
No, yeah, it was the exact word, but we used the, we deemed it correct if it was among the first 5 predicted.
So yeah, might it be more fair, for example, evaluated all the models on some subset of your word analogies test set, which included only words which are fully present in the vocabularies of all the models, like just skip the analogies where the correct answer is out of vocabulary?
Because you mean where the words are split into more than one token?
Yeah, so you have a set of word analogies, right? And you have some correct answers. And then why not just skip the analogies for which the model under evaluation doesn't really have a chance to produce a correct answer just because it doesn't have this full word in its vocabulary?
No, all the models have this ability to correctly predict the full word because it is split. There are no real out of vocabulary words. They are split into each word that is not in vocabulary is then split into subwords which are all in the vocabulary. But of course, it is much more difficult that's because it needs to correctly predict all these subwords.
Mm-hmm. Yep. Please.
Yes, I had a similar question, by the way, considering these fewer tokens to fill the mask, because I have worked on a topic where we needed to mask, to have just one mask, but we could be able to predict more than one subtoken. Just we generate and generate and generate until the end. So the question is, do you use many masks when you do word analogy, or you use just one mask and as like I explained, trying to generate more and more subtokens until you get the whole word? So how does it happen actually?
Yeah, so first we use the full sentence, which is not masked at all, and we tokenize it, and then we mask all those tokens which are part of the word. So there are exactly as many masks as the model needs to cover the word or to make the word. So if it is just one, so if the word is just one token, there will be one mask. If the word is split into 3 tokens, there will be 3 masks.
Okay, thank you.
Okay, we have more questions. Andrey also has another one.
No, we are not yet finished with the questions. My second question is, when you train this Litlat bird, did you use some corpus sampling like the creators of the multilingual bird did, or you just used all the text corpora that you had at your hands? So did you try to subsample the corpora according to their sizes?
No, we used all the corpora that we had available for Lithuanian and Latvian. And then we used the English Wikipedia for English just so that the amount of English corpus would be comparable to in the size of the two, did not have much larger English corpus. What we did balance.
So their sizes were comparable.
Yeah, the sizes, I don't know exactly right now. They're mentioned in the article.
But they were comparable at least, right?
Yes, they were comparable, yeah.
All right, then my question can be discarded. That's fine. Thank you.
Okay, let's thank the speaker again and conclude our session. Thank you everyone for coming here and for joining our Zoom meeting. See you tomorrow.
We should announce our roundtable. Right, so tomorrow we will start we will start at 11. Yeah, 11. But this will not be like a regular session. This will be a very thanks, Salah. This will be a very informal roundtable about the role of natural language processing track in the AIST conference. So where are we? Where are we going? Why are we here? And other philosophical questions. So yeah, feel free to join this this roundtable. I guess we will not probably stream it into YouTube, and we'll not even even record it, but it will still be available in Zoom. So online participants can still join, and we will discuss how to move forward with NLP at this conference. Yes, please join.